couldn't deploy anything. Yeah, nothing started, even though Kubernetes was kind of alive. And Googling a couple of hours, I ended up with a couple of links. Basically, the idea is that deployments do not create deployment pods, but instead deployments create replica sets, and then replica sets controller is responsible for creating deployment pods. And in our case, our cluster was almost died because of the lack of the resources, but still, to get into it, you should, I think, know Go just a little bit to be able to read what's happening, and this is clearly an exception in many of the key controllers inside the Kubernetes cluster. So, and super useful thing from my point of view, and if you are to take one thing from this presentation, I really think that it should be that one. So you can create your Docker image with all your favorite tools to diagnose, let's say, network issues, any other issues. And then you just run that Docker image inside your cluster with this command, and voila, you have a terminal access with all your favorite features, so you can see what's going on with that. Let's say why service is not responding and so on and so forth. And this is especially useful to debug some DNS issues inside Kubernetes. Yeah, choosing the right tools is an easy process, but rewarding. Why it's not easy, I showed you earlier the landscape. And we ended up with, these are the main important things. I mean, obviously not using just them, some others, but these are the most important things. So first of all, we were choosing between Customize and Helm. And I loved Customize because it's super easy, super straightforward. It's basically, you have a template and you have a substitution pattern. And voila, you have something like deployment descriptor for production, for staging, for developers. But we ended up with Helm because it provides even more than that. Packaging, dependency, and so on and so forth. We are using SCaFold from the developer's perspective for its dev loop thing. When you just run it and it starts to watch your microservices, if you change it, something, it automatically deploys it to the Kubernetes. Then Harbor is the thing for storing Docker images and Helm packages. Vault for credentials, Cert Manager for certificates, and finally GitHub Actions for CI/CD. And in Helm, also why it was, in the end we went with Helm, because in IntelliJ again, it's very nice support of Helm. You can see the actual values, so you can evaluate template and see the actual values in the end result. And also in runtime, it just shows you the actual value, automatically fetching it from the values file. And for the scaffold, as I said, it's very easy. You can describe the sandbox of your application, maybe the whole system or just a part of the system. Then you launch this dev loop thing. So it started to build everything, create Docker images, deploy them to Kubernetes. And then if you change something in the source code, so you don't need to compile nothing basically, you just change the focus, files change it, and then scaffold starts to rebuild and redeploy everything automatically. So you don't need to think about, just focus on the development process. And from DevOps perspective, it's also a useful thing. So this is how we integrate it with our CI/CD pipeline. It's basically just one line, and in the end, scaffold deploy, it takes the whole stuff and deploys it to whatever namespace we provided. Okay. And another real cool feature I would like to share with you, because I have experience with those. So maybe I will start with experience first. I worked for like 12 years in Germany in the research facility, and they also were kind of certificate authority, so you gave you certificates. But to get a certificate there, you make a request, then go on foot to a guy, show your ID, and then they issue a certificate. So now imagine you have like even 5 web-based microservices. How painful it is to do that kind of stuff. And this deployment actually is end-to-end automatization. So we have Rutgers, which is certificate authority in our case. So they deployed this ECMA thing, which stands for Automatic Certificate Management Environment, and providing credentials from, let's say, Vault. We obtain certificates automatically, and then with this just one line, cert manager cluster issue, we bind everything together, and so our services receive the new certificates, auto redeploy it, and everything works out of the box. And for this, we don't even need to develop our own anything. So it's purely a third-party driven thing, which is awesome. So lesson 6, try with some non-critical, non-continuous tasks. Maybe obvious thing, but still, I think worth to put in here. So we started with actually deploying our GitHub actions into our Kubernetes cluster, because we run the self-hosted environment. Very quickly we found out that the system is not very stable, and that was due to the basically lack of the resources of our initial test Kubernetes clusters. And continuing the previous lesson, but I wanted to highlight this one specifically because, again, previously I worked mainly for like using public open source services, never like self-hosted runners. And self-hosted runners give you almost unlimited possibilities. So you define your own Docker image. For instance, here in this case, we define the Java instance, so we can install whatever Java we want. Of course, we can do that with like this GitHub Actions thing, but that makes your GitHub Actions noisy, because for more or less for everything you need to set up Java, then you need to set up like Maven repository, something else, and here you just put everything in the Docker image, and it spins. You have already everything on board. Very cool. And final lesson, be prepared to invest time and resources into internal learning, because, as I said, Kubernetes is something completely different from what we experienced previously, and I firmly believe that developers must know the basics. Okay, some people say they don't need it, they just code, put it into the repositories, and we fetch everything, containerize, drop it into the Kubernetes, but I think the real power comes when everyone at least knows the basics and they can think about, because actually Kubernetes implies some architectural design decisions as well. I would say it's biased to serverless, but still, yeah. And the second point is actually saying that architects must leverage new design principles, so that they need to learn them and understand how it all works in Kubernetes. DevOps must be pretty advanced, because again, it's completely different from, let's say, running OpenStack. And yeah, you have to think about that as well. And yeah, so Kubernetes allows a lot of things. If you want a real benefit from them, you at least have to know about them. So I see like 2 possibilities to solve that issue. One of them would be to invite a third-party training company to do the training for your team, but in our case, we actually developed our own workshop, and I think this might be even more beneficial, because then you can really bind this workshop to the things that are happening in the team and already adjusted to processes you have and so on and so forth. So you will have much more engaged students, so to say. So we had like 3 tracks. First one is more like Docker oriented and how you deal with Docker. as a developer. The second one is more about Kubernetes itself. And the third one was about like advanced techniques like debugging inside Kubernetes or things like that. So it was a lot of fun. Everyone took their piece, just went through the track, and eventually finishing this with some rewards points, quite a lot of fun. And probably you will have to repeat that training several times. At this point, I would like to switch to challenges. And again, some of them are still open. So if you can provide any feedback, that would be great. So the first challenge is associated with our coastal distributed data centers, more or less. And in the very beginning, we were struggling between like multi-cluster thing versus cluster federation and a single cluster. Single cluster means that, we have nodes on west, we have nodes on east, and then using internal Kubernetes tools, just trying to, if a request comes to the east, then we try to stick to the east nodes, otherwise to the west. But in the end, due to some circumstances, we had to stay with multi-cluster solution, which is basically using have a dedicated cluster per coast, per data center. Another challenge is data storage. Again, we have these distributed data centers. We want to share data between them, obviously. We went with Ceph. I mean, this is still work in progress, and the storage is provided by San Diego Supercomputer Center team. It's not kind of in our control. But taking into account the nature of our data, which is mainly read-only, we also think to actually have like distributed file system and then local storages to each node, and that put the data into those local storages, and from microservices we are running actually read the data from the local storage, which should increase performance and reliability, hopefully. And another thing was we started with a Nexus repository to store our Docker images and Helm chart packages, but apparently it's not really friendly with Kubernetes, how it's called, role-based accounting something. Yeah, so we switched to Harbor eventually. And next thing was due to our Elastic setup. So as I said, we had a very fancy Elastic setup already in place, and on which we also created a lot of statistics about how our system performs, how it's used by the users, and so on and so forth. So obviously preserving that thing is hell of a challenge, especially in the fact that we used HA proxy and Kubernetes is more kind of Nginx biased, so yeah. And finally, there's like Java specific things. So since we are using Spring Boot, apparently it's not really friendly with being deployed as a subpath of the URL. So something like kubernetes.rcsb.org/app1, it doesn't work. You have to have like app1.kubernetes.rcsb.org. Well, yeah. So currently we have a workaround, just since we do not have much services, we just manually put everything into our DNS tables. And then in ingress, we just specify the specific host to match it to the actual service. But this one has a limitation if we want to go to namespaces. So for instance, we want to have production namespace, staging namespace, and a developer namespace that explodes very quickly. So we have to kind of define this DNS entry for almost everything, which is super annoying. So if you have solutions for that, that would be super awesome to learn about. And conclusions. So even though we had some like painful days and painful experience with it, still it's really cool. It's open a lot of, migrating to Kubernetes opens a lot of opportunity windows for using things like canary deployments, a lot of other flexibility, like fully continuous integration, continuous delivery pipelines, very easy to set up, and so on and so forth. So we're really happy we made that step, and that's awesome. I would like to thank our team at rcsbpdb.org. So this Jeremy, Jose, and Henry. It's really a team spirit, so you always feel like you're covered with anything. And also San Diego Supercomputer team, who actually provided us with a cluster and those services, so they did awesome job. So thank you so much. This is more or less mandatory slide because it lists all the fundings and all the group members of our team. And at this point, I would like to thank you for listening. And let's switch to the fun part. So questions, answers, comments?
If you want to raise your hand, I'll bring the microphone to you.
Thank you for giving the talk here. You mentioned concept maps at the beginning. Did you have a favorite tool that you used to build those or display them?
I'm sorry, favorite tool? Yeah. Oh, sorry. So the question is about favorite tools for the concept maps and things like that. Yes, we are using Miro.
Anybody else have questions?
I'm curious which Kubernetes platform you're using. Are you using like Rancher or OpenShift? Did you evaluate those as part of the process?
I'm sorry, so you're asking whether we evaluated Kubernetes platforms?
Yeah, like what distribution of Kubernetes are you running?
Yeah, as I said, we are not really in the control of that. So it's San Diego Supercomputer guys who actually, but they more, I think they did it more or less from scratch. So just took the raw thing and tried to play with it. Sorry, maybe I missed some information there, but.
Anybody else?
Sorry, I missed most of your talk, but I saw a slide where you said you have multiple Kubernetes clusters. So could you explain when you split your clusters, what defines your logic for creating multi-clusters?
I'm sorry, could you, it was difficult to me to hear. What are you asking?
Do you have one Kubernetes cluster or multiple Kubernetes clusters?
Yeah, so you're basically asking about this challenge we had, like, right?
Yes.
Yeah, so in the end, we ended up with a single cluster per host, per data center. So basically, then we need to duplicate all our, let's say, CI/CD pipelines, everything. So when we deploy, we say, okay, deploy to west, deploy to east.
Thank you.
Yeah.
Hello. As somebody who's looking to put Spring Boot into Kubernetes, can you elaborate a little bit more on the problems you had there?
So you are asking about this one, right?
Yeah.
Well, it's not much to say. When we just started to play with it, Ingress didn't work. So we Googled a little bit and quickly found out that Stack Overflow post, when it says explicitly that Spring Boot is not really a friend of URL path. So again, if you have something like your domain.com/app1, for instance, that won't work with Spring Boot. So Spring Boot requires app1.domain.com. This is kind of limitation. Maybe we could fix it somehow, but yeah, we were too lazy to do that.
I'm going to jump in here a little bit just because I have external knowledge and have worked on the program for the 2 cloud native tracks today, but Ingress has always been a little challenging with Kubernetes because it isn't quite fully standardized. They left options open with different implementations. And there is a talk this afternoon by Susan Wu of Google on a new thing that is just coming out called Gateway API So it is an attempt to put together a uniform API to accomplish what Ingress has. And if you're getting out there started with something new or maybe have had issues with the existing Ingress, that session this afternoon might be really of interest to you. Any other questions here? I'm going to jump in with a question just because I'm curious as to what the hardware you're running looks like. Is it, you know, supercomputers implies these are like super powerful things, maybe not standard, but are they on x86, on ARM, some mixture, and do you have GPUs and AI machine learning accelerators thrown into the mix for what you're trying to manage workloads for here?
Yeah. Thanks for the question. Great one. Well, I'm not the right guy to ask that kind of questions. I just can share my feeling because, again, I'm just a part of the San Diego Supercomputer Center. I have a feeling that they also started that kind of process of migration to Kubernetes. Obviously, as a supercomputer center, we have a lot of hardware, like specifically for GPU tasks, for some other computing ideas driven by the scientist community who actually come to us and say, okay, I have such and such computational problem, so to say, to solve, and we say, okay, we will deploy such and such a solution for you so you can use it. And far as I know, they are now going to really move to Kubernetes more and more of those high-performance computing things. So in our case, I believe it's just an ordinary server in some racks, a couple of them, so nothing really
Okay, thank you.
fancy.
Any other questions? I'll throw it out there too. It doesn't just have to be questions. I was chatting with some of you in the audience before, and I know some of you are either on journeys like this with other institutions or maybe are thinking of it. If you've got any comments or observation, maybe we can turn this fully interactive and you can tell us what your interests are or what your observations are if you want to raise your hand and share.
Your challenge around DNS, I was curious what your DNS provider looks like. I've used external DNS in the past, and that is super useful for managing the different.
So we are using NS1 as external DNS, which points to our entry points, and then hopefully Kubernetes will deal with the stuff inside it. But I mean, yeah, to actually achieve that, we had to, provide. So these are inside NS1 entries, and then, we configure ingress this way for Kubernetes to actually be able to point this entry point to a specific service.
Last call, any questions or comments, observations? Okay, well, I appreciated the SCaLE conference is all volunteer driven. We get people like Igor coming here who don't get paid to give these talks. If you, like I do, think that this was great and appreciate it, could you join me in giving him a round of applause?
Thank you.
And thanks. We've got a full day of tracks in 2 rooms related to cloud native. One of the big values of this is to meet people in the hallways as well. And if you're first time to SCaLE, feel free to chat with me about other things to do. I would definitely encourage you to stick around for some of the social events too, like Saturday evening has dinner, board games, and sometimes some of the best experience I've had over the years are joining in on those kinds of things. The exhibit halls are going to be open this afternoon, and if you're local to the area, sometimes people don't notice this, but on Saturday, we are one of the few conferences that are open to families and children. We have a whole track called Next Generation, which is under 18 speakers, and we have sessions designed to teach kids tech with hands-on experiences. So if you're in the area and you have family locally, keep that in mind, because that's a pretty unique opportunity, unique to this conference. And if you already registered, the kids registration is totally free. And like I say, they have some really cool workshops. There's even a games night for kids set aside for under 18 plus their parents who accompany them. And there usually have been prizes. I haven't looked at it, but that's going on here. There's a lot of other stuff going on, so look at the schedule and look at that kind of stuff. And thank you for coming.
Testing, testing.
Check, check, 1, 2. Hi, everybody. Oh, there's yes. Checking 1, 2. Turn on that mic again, and let's see. Check, check. Sometimes when you get these close together, they have too much gain on. Check, check.
Check,
1,
check.
2.
Check, check. Handheld.
Check,
Check
check.
1, 1, 2. Check, check.
We're okay now. Checking 1, 2. Oh, right when I cross here. Okay, checking 1, 2. Yeah, I mean, I think checking 1, 2. Yeah, can they, so on your end, can they bring down the checking 1, 2, check 1, 2. Hi, everybody. It's okay, we're good. Checking 1, 2. Mic check 1, 2, mic check 1, 2, mic check 1, 2. I think that's good.
there been a binary was invoked, we can actually see some permission checks against the EC password. To connect to a netcat listener, and then it's going to send over a reverse shell. So I will switch back to the terminal, set up this LDAP server, and then set up the netcat listener, and then later
Put that in a pocket or somewhere that's convenient for you. Ivanko, yes?
Ivanko. but
Ivanko,
It's
okay.
fine. Wait a minute.
You have 50 minutes, including Q&A. So, and when we go to Q&A, I'll take questions with the mic, so
Cool.
it gets on the recording.
Yeah.
So you ready?
Yeah, go ahead. I mean, let's wait for the people.
Okay. Yeah, and people are still wondering when this happens here. Welcome, everybody. If you can get situated, we'll go ahead and get started. Let me introduce Natalia Ivanko, who is going to explain to us how we can prevent the next Log4j using eBPF. Natalia's co-presenter, John, couldn't make it, so she's carrying the whole talk by herself. So let's give her a big welcome.
Cool. So welcome. Wait. Okay.
There we go.
Okay, so welcome everyone and thank you for coming. So today we are going to talk about Log4jshell and then preparing CVEs or the next CVEs with eBPF. So my name is Natalia Ivanko. I'm a security product lead at Iceland, and then John today couldn't make it, but let's give him some credit. He's a Tetragon lead, a Cilium maintainer, a long-time kernel engineer, and then a staff engineer at Iceland. So a little bit about like motivation and then the agenda today. So first we will talk about like what is Log4jshell, like why is it so powerful, and then how eBPF comes into the picture, like what is eBPF, why eBPF, and then we will take a look into like one project which provide eBPF-based runtime security. This is going to be Tetragon, and then we will see a demo, like how Log4jshell would have been cut with Tetragon, and then we will see some further detection and then prevention techniques. So first, Log4jshell one-on-one, it's going to be like a nutshell, like not really a deep dive. So what is Log4jshell? So it's basically a vulnerability. It's a vulnerability in a logging library, a Java-based logging library, which allows remote code execution. So it basically allows an attacker who actually controls the log messages to execute arbitrary code on a server. So how does it work, and like what Log4jshell features allows to do that? So first of all, the Log4j library allows to log messages, like text messages from sources that you don't control. So for example, if you have like an application and then it's receiving data, it logs like what was the error code, what was the return code, like was it successful, was it not successful, and so on. The second one is basically, it allows you to log environment variables. So you could log the OS version, the Java version. So you could do like something $curly brace, Java version, and then curly brace. And then basically it will log the Java version. And then you could do that recursively. So if that Java version string contained like something $curly brace, something curly brace, it will replace that and then log it. So now I can actually craft strings very creatively, and then basically the application will log data that it doesn't seem like it was logging. And then the third one is actually not related to Log4j. It's another Java feature. It's GNDI Java name and directory interface feature. So it allows you to look up information on other servers. So basically, you could do DNS lookups, you could do LDAP lookups. So you could do something which is like on point A. So you could put like GNDI LDAP, you put the server name, and then what Log4j will do that, it will go to the server, look up that information and return. And then basically the last one, which is, yeah, I don't understand like why. So it can return with a Java object and then basically run it. So for example, if that LDAP server contains like a Java object, Log4j will just download that Java object and will happily run it. So how would it work? And then we will see it in the demo, like step by step. So let's say I'm an attacker. I actually have like an LDAP server set up, and then I control it. I put like a malicious Java class file on it, and then I have another machine which I run netcat listener. And then I discovered like there is a vulnerable web application, and then it's running like a vulnerable Log4j version. So this web application is exposed to the internet via a static IP, via a load balancer. And now let's see what I can do. So I can actually send the malicious string to the application. So let's say GNDI LDAP, and then I put the LDAP server name. So what the web application will do, it will actually, like the Log4j library that the application is using, it will actually parse the string and then resolve the IB and then connect to the LDAP server. And then you can see the LDAP request, and then the LDAP server will respond, and then it will contain the exploit.class. And then what the web application will do, of course, it will just happily run that exploit.class, and then we'll execute the code what was inside the exploit.class. Like in this case, it was a reverse shell, and then we will basically see the reverse shell that was sent to the netcat listener. So that's basically how Log4j works, like in a one-on-one, not very deep, but good for like a very good explanation. So why is it so powerful? So we can see the first one, it's like really easy to exploit. Like I can just craft a string, set up a server, send that string to the application, and then it will connect to my server. And then it's due to the features that I mentioned before. And then it basically enables remote code execution, so I can run whatever I want. And then I'm not a Java developer, but I talk to my friends who are Java developers. It's basically everywhere. Like if you are using Java, like there is a high chance that you are going to use this library. And let me know if I missed anything. So what could detections and response team do? Of course, patch these systems and then identify like what should they patch. But it will take like very long time. Until this is like broadly completed, they should make sure that the Kubernetes workloads or the servers that they are running are safe, and then they should detect if they have been compromised. So for this, they would need visibility into Kubernetes workloads, services, VMs, whatever they are running, like what happened, when happened, why happened, what the attacker did later. And then they would need to do that in real time, kind of real time, and then also with a low overhead. So that's what we would like to achieve. And then this is how eBPF comes into the picture, and then basically what is eBPF, and then how could it help to us. So before diving into eBPF, I would do like a basic kernel architecture one-on-one, not very deep. I'm not a kernel engineer. You would need to ask John, who is not here today. So basically, we have three spaces. User space on the top, Linux kernel in the middle, and basically hardware on the top. I put storage and network here. There is many more, but I wanted to simplify it as much as I could. So what the Linux kernel will do as a very first step, it will abstract these hardwares away by using so-called drivers. So basically, the Linux kernel needs to be aware of hardware and enable it, but it doesn't necessarily need to expose that logic directly to the user space. So it will use so-called drivers and say like, hey, I'm aware of network devices. I'm aware of like storage devices. I'm aware of console. I'm aware of I/O. And then similarly on the user space, we have a notion of process, an agent, a user space application, and then how that user space application communicates with the kernel, it's via system calls. So for example, if you would like to do like a file I/O, you would use syswrite, sysread. You can use also send message and receive message. So these system calls are related to network connections, so this would be done when opening a TCP socket. And then basically we have the middleware, the business logic in the middle. So this is basically like virtual file system, the process scheduler, TCP/IP, firewall technology, and so on. So what if I would like to change that logic? So what if, for example, I am an application developer, and then I would like to include in the new feature that would provide visibility and observability into my Kubernetes workloads or observe my application. So I can go to a kernel engineer and then say like, hey, can you implement this new kernel feature for me? And then he will say like, yeah, let me just code that for you. So it will take some time, months, years, but once it's implemented, it's a step ahead, but they need to convince the entire kernel community that the changes that he actually included for me, it's actually useful, it's needed, and then all the world should be paying the cost and the complexity for his feature that he is adding. But once he convinced the entire community, it's good, the changes are in. So now, as I'm an application developer, I should convince my users to upgrade to the latest Linux kernel, which is, depending on the users, take years. So, but after, I don't know, years, 5 years, they upgraded to the latest Linux kernel, and then it's fine. But the problem here is like, nobody got like 5 years, and then probably my requirements have changed since then. So how eBPF can help here? So what eBPF allows to do us, it's like pretty amazing. So if you remember like a couple of slides earlier, I talked about how user space applications communicates with the Linux kernel. So it's via system calls. And then what eBPF allows to do is actually we can take over that system call and run a BPF program on behalf of it and then return. So I put exequa here, but we can take a look at other example as well. So exequa is used to launch a new process. So what we can do, we can run a BPF program on the return on the exequa and then extract some information. So I put bit here, binary name, and then com, but we can include much more. So we extract this type of information, and then we can export it to user space. So this is, for example, how application profiling and tracing works. But how does it actually work exactly? Like, how can we run code inside the Linux kernel? So first of all, like in the very beginning, there is bytecode. So this is actually the compiled version of the code that I showed you before. So let's say we would like to run this code in the return of every exequa system call. So first of all, we use the BPF system call to load that program. And then once it's loaded, it goes to the verifier. So the verifier actually makes sure that this code is not buggy, it won't crash the Linux kernel, and then if it's buggy, and then it will crash the Linux kernel, then the verifier will reject it, and then it's not going to load. And then once it's approved, it's going to go to the JIT compiler, the just-in-time compiler. So at that time, the bytecode is really generic, so it can run on ARM, x86, whatever. And then it will take that code and then compile it to the native architecture that your CPU runs. And then once it's completed, we can attach it to the return of the execute system call. And then, so where can we hook? Where can we attach BPF programs? So I only talked about system calls, but there is like so many more. So if we take a look at starting from the top, we can actually attach to user space application by using uprobes, like user space probes. So if your application have a function, we can just like hook on that function and execute BPF code. Of course, we can attach to system calls, kernel functions, trace points, which are like more well-defined in the kernel. And then we can take it actually down to the hardware level and then, for example, upload it to the network driver. So whenever like a packet is going to be received, you can run a BPF program. And then what's really important, so it's completely unrelated to the information. So if my BPF program is actually modifying packets or like receiving packets, the last packet will not receive that modification before the BPF program was loaded, but once you actually load the BPF program, the next packet will actually receive it. Okay, so now we can run BPF programs, but like, what can they do? Like, how do they actually communicate with user space? So it's important that BPF programs are only the instructions. So there is no state, there is no memory allocated dynamically. And then any state is stored in BPF maps. So for example, the metrics, the statistics, the data, you actually put it into like a BPF map. And then I listed a bunch of one here, like hash tables, arrays, ring buffers, stack trace, longest prefix match, least recently used, and so on. And then also like user space applications can read from that map. So for example, if you have like an agent or a CLI, it also reads from that map. And then it's also important like these maps are completely separated from the programs. So whenever you replace the programs, the map will stay alive. Okay, so now how the development would look like with eBPF. So I'm an application developer. I can just go to like an eBPF developer and ask him like, hey, can you just like include this Linux kernel change? And then he will just do that in a couple of weeks, months, depending on the engineer, release a new version of the eBPF project, and then I can happily use it, and I don't even need to reboot my machine. So it's actually, eBPF is actually became like widely used. It's cross-platform. Recently with the Windows runtime, most Linux distros supports it, and then basically all the major cloud providers. And there are a bunch of projects which are using it under the hood for different kind of use cases. I put 3 examples here and a couple of projects, but there are so much many more. So this would just give you a glimpse, like what can we do with eBPF, but there is a lot more out there. So for networking, it's mainly used for high performance and load balancing. So there is Catram, which is like a high performance load balancer from Facebook. So they switched to eBPF instead of IPVS, which is like a software-based type of load balancer, and they saw a massive performance improvement. So we have Cilium, which is like load balancing, networking, and security for like Kubernetes services. On the observability side, there are use cases like application tracing, performance troubleshooting, and monitoring. So the first two is BCC and BPF trace. So these are applications like figuring out what my application is doing, what my system is doing, why is it not behaving the way it should or the way I expect. We have Hubble, which is the visibility component of Cilium. So it's mostly for like network policy troubleshooting, like why my network flows are dropping, by which policy, why is it not allowed, why is it denied, and so on. And then on the security, like we will deep dive into Tetragon later, but you can use BPF for container runtime security. So basically, we have Tetragon, Tracy,
and Falco here, but I just put 3 examples, but there are many out there. So you could hook like any kernel function or system call and then figure out or like detect if any suspicious behavior happened. And then you could implement also like least privilege policies. So observe all the system calls and kernel functions, network connections, file I/O that your workload should be doing, create a policy, and then basically prevent everything else. And then you could use that also for preventative security. So you could terminate on malicious activity inside the kernel. So I will talk about like eBPF-based runtime security with Tetragon that we are working on. So what is this exactly? So it's like an open source project. It's an agent that it can run on the top of any Linux operating system. So in case of Kubernetes, it's actually a daemon set, and then in case of like Linux VMs, like bare metal VMs, it's actually a container, or it can run as a systemd service as well. So it basically mounts a bunch of configuration files like policies, which will generate security observability events. So there are a lot of layers where we can extract data from. So starting from the bottom, data access and then file access. For network, we have a variety of ASM parsers, HTTP, DNS, TLS. We have visibility into kernel namespace changes, capability changes, and then privilege escalation. We have also visibility into like process execution and then system call activity. So all those events that you would observe with eBPF would go into a log file as JSON events. I will show you an example later. And that log file basically later can go to any CM system, Splunk, Elasticsearch, Sumo Logic. You can export it to S3. And then basically we have metrics like Prometheus, Grafana. These are mostly the networking use cases. So what events do we care about? So if you would observe like a malicious activity, it would do at least one of these things like network traffic, file I/O, running executables, system call activity, changing privileges, and then namespace boundaries. So this is actually how JSON event would look like. This is actually just picking up like TLS v1, which is like an old TLS version, and then we should never use it. So it contains like the Kubernetes identity information like workloads, pods, namespaces, labels. It has the process visibility information like what binary was running, like with what argument. It also includes like network connection data like source IP, destination IP, the ports, and then in some cases DNS server metadata. And then for post-processing, either you can just like ship it to a CM system like whatever you have, or you can like observe these events like via CLI, which is like more visual. That's what I'm going to do in the demo. All right, so how can we actually detect Log4jshell with Tetragon? So I will just introduce the test environment, talk a little bit about it, and then I will play a video. I won't do it live, I'm sorry. So yeah. So how the test environment would look like. So as I said, Tetragon can run on any Kubernetes nodes or Kubernetes environments and as a daemon set, or in VMs as a container or a systemd managed service. In the demo, I'm just going to use a VM. I deploy it as a systemd managed service. I will apply security policies, which will actually observe network connections via TCP connect and TCP close. It will observe like file I/O, write with syswrite, and then basically file open and close with sysopen and then sysclose. And then how the Log4j setup would look like. So I actually exposed this VM via an external IP. So I set this IP to static instead of ephemeral. So we can actually like reach it from the outside. And then I have a web application running on localhost 8080. I have a fake LDAP server as a container running on 1.3 89 port. This will be important later. And then I also set up the netcat listener on the same machine on port 9001. And then I have Tetragon as not a container, but a systemd managed service. So let me just quickly try to play the video.
Cool. So let's jump right into the demo. I'm going to use a testing Ubuntu VM 12.0 for LTS and Google Cloud. This is the SCaLE 2023 Log4j eBPF VM that we can see on the bottom. We can see the internal IP 10.186.024, and then we can also see the external IP. And then what's really important, I set this IP to static instead of like an ephemeral IP, so we can actually reach it from the outside. And all the demo are going to be run in this VM. So let me just switch to the terminal. And then we can see basically 3 sessions here. All the sessions are actually inside the VM, so I SSH'd into the VM. So Tetragon is running as a standalone version here. So instead of like a daemon set or a container, it's actually running as a systemd managed service. So let me just quickly check the status. So all the Tetragon related information will be displayed on the bottom terminal. So if I run systemctl status, we can actually see that the service is running. We can also see that it's managed by systemd. And then if we scroll to the bottom, we can actually see that it's listening for events. So I already applied the policies which would actually observe the TCP connect, the TCP close, syswrite, sysread, and as well as the sysclose for certain files. So let me just try to observe the events first and then show you a couple of examples. So let me just try to observe the events, and then we can already see a couple of Google related ones. And then on the second terminal, I can actually run like ls-l. And then we can see that the user bin ls binary was invoked. We can actually see some permission checks against the EC password file to be able to see whether the binary has permissions to actually list the directories and the files. And then we can actually see that the process exited. All right, so let me stop observing the event. And then next, what I'm going to do, I will actually start the vulnerable web application, which actually contains a vulnerable log4j version. So it's going to run as a Docker container on the host network. So let me do that in the top terminal. All right, so we can actually see that the container was created. And then let me try to list it. All right, so we can see it's running. So I can actually try to open it from the browser because it's actually using the host network, which would actually use the external static IP of the Ubuntu VM. So let me quickly change to the browser again. And then since it's listening to port 8080, I can actually try to open it. All right, so this is how our vulnerable web application looks like. So it's actually, as I said, contains the vulnerable log4j library. So in theory, if we would send a string to this application, which contains a GND lookup to a malicious LDAP server, it actually would resolve that connections while logging this string. And then basically it would connect over the internet to that malicious LDAP server, download the malicious Java class file and execute it. And then basically the malicious Java class file would do whatever we want it to do. In our case, it's just going to connect to a netcat listener, and then it's going to send over a reverse shell. So I will switch back to the terminal, set up this LDAP server, and then set up the netcat listener, and then later we will send this malicious string to this web application. So let me switch back to the terminal, and then I will make some space. Great. So let me just start the netcat listener first, and I will also start observing the events so we can actually see what's happening. So let me start the netcat listener. We can already see that Tetragon actually picked it up. And then I will also start the malicious LDAP server. It's actually using a Python script. And then, yeah, so we can see a bunch of Tetragon related events. I will go through over it later. And then let's take a moment to appreciate what we can see on the top terminal. So I took all this POC from a GitHub repository from Cosmer. It's actually great, pretty easy to use for testing and also trying out different kind of stuff. So basically, this Python script set up the vulnerable LDAP server and then basically created a string for us. And then we can see that it's listening on port 1389. This is going to be important later. And then it also created the malicious Java class file, the exploit.class. And then if you take a look at the Tetragon events on the bottom, we can actually see in details what happened. So here we can see that the Python script started, and then it basically invoked a bunch of Java binary file. We can actually see that it created the exploit.java class file, and then basically we can see that the process exited. So with exit code 0, so we can actually see that it was successful. And then we can also see that it copied a bunch of other related files that we will need for this exploit. All right, and these are the Google events that we saw before. So let me try to send this string to the web application. And then in theory, we would see that there was a connection here, and then we would actually see that we got a reverse shell on the netcat listener. So let me try to switch back to the browser and send the string. And then the password, I can say whatever we want to say. I will say welcome to SCaLE 20x. And then let me click on login. So in theory, we should, and then actually we see that there was a connection to the LDAP server as an LDAP request, and then it actually downloaded the exploit.class malicious Java class file, and then we can actually see the LDAP response with the return code 200. So we can actually see that it was successful. We can actually see the reverse shell that picked up or the netcat listener that picked up the reverse shell. You can see the connection was received. And then on the Tetragon side, what are the related events for the malicious LDAP connection? We can actually see that there was a JREP in Java binary that connected the localhost port 1389. So this is our malicious LDAP server. And then in theory, this can be actually like an attacker controlled machine. For a testing environment, I just set up every single localhost because that was easier. We can actually see that the connection was closed, and then we can actually see another connection to port 9001. And then basically this is our netcat listener. And then here we can actually see the vNSH process that was executed. That's actually our reverse shell. So this was, again, against the LDAP server, this was against the netcat listener, and this is basically the reverse shell we got. So as an example, let me try to execute some commands. We can do, for example, ls-l. We can see that we are actually inside the web application container. I can try to read cat etc password. We can actually see that the binary binary was invoked. It checked against some permissions against etc password file, that it has permissions to read that files. We can actually see that the cat process with which I was actually reading the etc password. We can actually see the open and close events. We can see the exit. And then I can do the same, for example, with etc shadow. And then basically we would see the same events. So we can see that the cat process started, etc password file was open and closed, and then we can see that the cat process was actually exited. So as a last step, I will try to edit etc password, but I don't think I have Vim or any text editor installed. So let me just try to install this inside from the container. So let's just update the packages first, and then basically we can see all the Tetragon related events here. So these events are actually really powerful if you export it to a CM system like Alco or for example to an S3 bucket, because you can create like signatures to detect attacks, or you can actually follow what the attacker was doing during exploiting this container. So let me install Vim. And then I will continue, and then I will install the packages. Alright, so now I have Vim installed. So let me try to edit etc password. And then we will see an event for the syswrite system call. And then we will see basically the file and then the content of the bytes, or the number of the bytes that was written into it. Alright, so I can try to add like Natalia. And then I can actually save it. And then what we can see in the bottom, that there was the Vim process invoked, and then basically there was a bunch of open and close because Vim is very noisy. And then basically here is the write event with the file and actually the number of the bytes. So you could do, for example, more maestro stuff like adding an SSH key or invoking a network connections, whatever basically we want to do. But this is just like a small proof of concept demo, like how Tetragon could have detected Log4j, and then we will include other prevention techniques and other detection techniques for upcoming CVEs, because there is going to be a bunch of ones in the wrapping up section.
Okay, cool. So that was the demo. And then, wait, let me just switch back to the slides. Yeah, okay. No. Yeah, should be fine now. Okay. No? Yeah, I think it's fine. Yeah, okay. Yeah, so let me just try to switch back to the slides. Cool, so the CLI actually didn't display all the information that, for example, that JSON events would take, and then, so if you would export to like a CM system, as I said, or like an S3 bucket, you could actually do more powerful stuff. You could create like signatures for detection, because as I said, It includes all the process-related information, then basically process lifecycle for pods and host processes, all ingress and egress network connections, and then basically file accesses. So you could create, like this is just a very simple example with a Splunk query. You could create signatures for shell execution. So you could actually match on like when a shell was executed inside your Kubernetes workload or a pod, which should be very malicious and should be never done. You could detect, for example, late process execution, which is also pretty interesting. So you could pick up like events what were executed 5 minutes later or like 10 minutes later your container started. So you would say like, hey, my malicious Java or like my Java application should never reach out to that LDAP server because that would be, I don't know, after 5 or 10 minutes later. You could also monitor for like leaking environment variables. So I mentioned in the beginning that Log4j allows to resolve variables like recursively. So this, for example, would actually log the user environment variable on the server side. So you could actually create a Splunk signature by matching on user bin env, which will be executed. So this is like when dumping environment variables. And then, so for prevention, I would apply the least privilege principle for network connections. So only allow the network connections that your application needs and basically no more. So this would actually prevent the malicious LDAP reach out from the Java binary. And then for this, you could actually use, or I would actually use Cilium network policies. And then I would take advantage of like 2 main features, the DNS-based policies. So this would allow traffic based on a fully qualified domain name, such as api.twitter.com, in place of like IP siders, IPs, and then endpoints. And then the second one is basically deny policies. So you can define like a set of destinations that will be denied by that policy by allow anything else. And then you can also say like word, which defines like every host on the internet. So there is like a concept of word in the deny policies. So there are 2 pieces here. The first is basically allows connections only to api.twitter.com. So let's say I have like an application and then I only need to connect to api.twitter.com. So the first policy will do that. And then the second will basically do like an egress lockdown, so deny everything else. So wrapping up, so a little bit of recap. So we saw like a little bit of like 101 Log4jshell in a nutshell, like why is it so powerful, and then how does it work. We saw like what is eBPF, how it comes to the picture, how it provides like full visibility into Kubernetes workloads and then VMs. We saw that it's low overhead, real time, and then we saw like what kind of visibility we can do, like process, network, IO, capabilities, namespace changes. We saw an example with Tetragon, and then see how could it have caught Log4j, and then we talked a bit about like further detection and prevention techniques. So lastly, so we are working on like Cilium Tetragon, so how to contribute. Go to the GitHub repository, join the Slack channel, use the tool, report bugs, we have bugs, create feature requests, tell your user experience. We have like a bunch of layers of the stack that you can work on, like Golang and then documentation, systems, BPF side, Linux kernel, and then packaging. And then, yeah, thank you again for coming, and then it's Q&A.
Hi, it was a great presentation.
Okay.
I have 2 questions. Number 1, do the eBPF programs intercept the syscalls, or do they simply observe them? And second question is, you mentioned that there was a
like a lint checker or a sanity checker before they got compiled. How exactly does that work, and how does that know what is good and what is bad for the kernel?
Okay, so the first one, we actually like intercept the system calls. We can look at like f entry and then f exit. And then going deeper for the verifier, you would need to ask John. Like I know that it's checking for like instructions and then like looking for kind of bugs, but in deep details, I don't know. But I can actually like follow up with John and then make sure.
More questions?
Hey, there is one. Over.
Thanks for the presentation. You had a slide earlier where you showed some other eBPF projects. There was logos but no names, and I didn't catch what they all were.
I can go back. Yeah,
Thanks.
this one.
Yeah, he was asking what the names of those projects are?
Wait, what? Which means what?
The names of the projects.
Name of the project. Okay, so it's like Catran, Cilium, BCC, BPF trace, Hubble, Tetragon, Tracy, Falco. I can also like follow up later on the names, but if you go to like eBPF.io, and then like this is the main website for eBPF, and then you can just like find a bunch of materials there, and then there will be like a landscape, and then you will see all these applications and like 50 other more.
Okay. Do we have other questions?
One more.
Hi, I was just curious if there was any evidence of this detecting Log4jshell before the CVE was announced?
Before?
Before the CVE was announced?
Yeah, I mean, so you could see all the events, like, hey, if you have like a web application, you could see, for example, the malicious like reach out. Like you could see everything, but then like you wouldn't call it like Log4j. So, you know, you don't have the name. Like if the next CVE would come up like whatever, like you would see all these events, it's just like the name will come like next day or like whatever. So yeah. So it's basically just like, really just the kernel functions and then the system calls that we are basically hooking on.
One more question? Okay, well, thank you very much, Natalia, for a terrific talk. Great. A couple things. We're going to have a 1 hour break for lunch. Lunch is up to you, and then we will continue in this room and also Ballroom H at 1 o'clock. So see you then. There's also been a schedule change in this room. The session at 5:15 is being replaced with a Kubernetes Home Lab BOF because the speaker did not make it here. Thanks.
just turn on the countryman sitting here on the table, and it starts to ring. Pa, pa. Check, 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 check. This is the country. Check, 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 check. Can you still hear me in the back okay? Sounds good. Okay, Mike, that's better. Mike, that is better.
The frequency is out because it sounds like it's ringing on the low frequency. So keep talking, and I'm going to bring back up channel 1 to a higher volume and see if we corrected that low frequency feedback.
That's what okay, great. You guys are working on lowering the low frequencies on your end then. So we're talking right now, it's sounding better. We're not hearing it. Checking 1, 2, I'm gonna move around a little bit. Checking 1, 2, checking right here. I think it's reflecting off of that, honestly. Checking 1, 2, checking 1, 2. I mean, how many people are coming down here? They're mostly up here, right, talking? Yeah, up here it has, I don't believe it's been a problem. Everybody can hear me back there. Yeah, I'd bring the level down just a hair. Just get some slap back from the back wall. So we're still checking, and we're checking 1, 2, checking 1, 2, checking 1, 2. Checking 1, 2. I might drop it just a hair more volume-wise, because it's really slapping off the back, and even if they're soft talkers, people can hear back there. Hi. Hi, everybody. I'm a soft talker, but you can hear me. I think we're getting in the zone there. Everybody happy? Are you still making adjustments on your end? For room G? Okay, great. I think we're in good shape. Thank you. Perfect. Okay. And this one seems pretty strong on the levels. This is mic 2, the handheld mic. I think we could probably cut this down a little bit as well, please. So we're still working on microphone 2, input 2, the handheld mic. And you guys are bringing it down a hair. Checking 1, 2. Yeah, this room's a lot of slap back in this room for some reason. So we're wanting it down a little bit more in this room. If you wouldn't mind dropping the volume in the room down a little bit more on mic 2. Checking mic 2, we're soft talkers. You can still hear us out there, yes. Checking 2, 2. That sounded pretty good, yes? Okay, I think we're good in G then. Thank you. Okay, we will. Standing by in G. Would you like me talking still? So this is for microphone 2. You're talking about the handheld, correct? Checking mic 2. This is handheld mic 2. Handheld mic 2. We're talking at a fairly normal voice. Checking. Checking 1, 2. Checking the mic 1, 2. We're checking our audio levels here to make sure everything's working pretty well. Okay. Yeah, this room's very echoey. Checking 1, 2. Let's just adjust these speakers slightly, see if that helps. It's okay, this one will be fine. Let's try this. I'm not sure, it's just slapping off the back of that wall. How are our volumes back here? Maybe we just want to drop it all a little bit. Checking 1, 2. No, just the in-room volume. You know, it's not really that loud over here. You have no bodies in here, so when you have some bodies, hopefully that'll take. I don't know why this room's so echoey. Let's turn this speaker a little bit too. See if that keeps it off the walls a little bit more. Checking 1, 2. I don't know. Yeah.
we go, try it out.
Testing. Great. You can all hear me? It's not rustling my beard? Okay.
Okay, welcome everybody to the afternoon of Kubernetes Community Day Los Angeles. And next up, we're going to have Taylor Thomas, who's going to explain to us how we're all going to be using WebAssembly in the future if we're not already. So welcome, Taylor.
Awesome, thank you. Well, thanks for the introduction. Hopefully I keep all of you entertained and excited to get past that post-lunch coma right now. So yeah, as introduced, my name's Taylor Thomas. This talk is called WebAssembly, a Recovering Kubernetes Engineer's View of the Future. So I just want to start off with, the classic, who am I? I'm a director of engineering at Cosmonic. We're a startup. We work in the WebAssembly space. You'll see a little bit of what we do during this, but I am a Rustation. I got there by way of being a gopher. And I mean, I write in all sorts of languages all the time, but Rust is probably my favorite right now. I was the co-creator of the Crustlet project, which was one of the first projects out there to try to get WebAssembly and Kubernetes to play nice together. And also another project called Bindle. I'm a serial open source maintainer in general. I'm an emeritus Helm maintainer, which I'll talk a little bit more about in a second. And I'm also a core and project maintainer for the Wasm Cloud project, which is I'm going to talk a bunch about today. So normally, I don't like to really toot my own horn too much, but I wanted to give a little bit of history about where I'm coming from. So this is kind of the slide where I explain this is why my opinion hopefully matters in this talk. I got started with Docker around like version 0.6-ish, somewhere around there. I can't remember the exact one. And I've worked with Kubernetes since 1.2. So I've been in since almost the beginning with it, done a lot of stuff. I built Kubernetes platforms before Kubernetes platforms were a thing at Intel, Nike, and then I helped build AKS at Microsoft. And I'm not trying, like I said, there's plenty of people who I built these with, but this is where I'm coming from with it. And I was a core maintainer of Helm for 4 years. And my deepest, darkest secret is that I wrote the wait flag. So if you are a heavy Kubernetes user and you know what I mean, you probably either want to throw a rotten tomato at me right now, or you want to come shake my hand. And if you're in that latter group, you probably should want to throw a rotten tomato at me because, boy, is that a landmine. Anyway, so that's my deepest, darkest secret. I've done in the Kubernetes space, but I've done this for a while. And like I said, I just wanted to explain that I'm coming from a place where I get it. I've done Kubernetes. I've done everything from controllers and operators and CRDs and built custom scheduling components and written Helm. With Helm, I wrote a good chunk of Helm 3 along with a couple of the other maintainers. Did Helm 2 for a long time before that. So there's I understand this space and I understand a lot of the pain points that are in it, and so I just want to say I really sympathize with that. But I also come from the WebAssembly space. Like I said, I helped create Crustlet with my former team before I worked at Cosmonic. And I really have been involved just deeply in WebAssembly for the past 3 years. Been involved in Wasm Cloud, a bunch of community projects. And so I want to use that knowledge to kind of explain where we're going, how this works together, what things are supposed to work, what things don't really work, all that kind of stuff. I'm trying to cover all of that today. And we are going to be very demo heavy. We're going to do some explaining and then some demoing and a little bit more explaining and tons of demoing. So I did not have a ram stick with which to cut my hand to do the blood sacrifice to the demo gods. So who knows what will actually happen, but it will be a live demo for all of this. So let's go ahead and talk about what's this Wasm thing. So just out of curiosity, how many people have done anything with WebAssembly more than just read about it? Okay, that's pretty decent. That's a little bit more than I was expecting, maybe about a quarter of the room for those on the stream. So I'm using that to kind of tailor this response to talk about what is WebAssembly. So if you've paid attention at all, you've probably seen a lot of in the WebAssembly community say this exact statement. It's neither web nor assembly, so it doesn't really make any sense, the name. It's not meant to, it's not just a web technology, and it's not really assembly, but it's just happened to be the name that it came with. And it really got a start in the web. And the reason why it was so popular in the web are these reasons right here. And to kind of dive into that a little bit, is that it's an open W3C standard. So that's kind of a basic thing for anything on the web. And so it comes from a standard, the standards group, and is supported that way. It's also safe and secure. Because this is browser code we're talking about, you have to sandbox. There's no wiggling around that. So you have to be able to work in a sandbox, and it uses a capabilities permission model. If you're not familiar with that, that's what happens on pretty much any phone nowadays. Do you want this app to access your microphone? Do you want it to access your camera? That's capability-driven permission models. Then you have the idea of it being efficient and fast. So the people who are really using WebAssembly are people who had big, like, front-end applications. Think like Photoshop, AutoCAD, all those things. They use WebAssembly to actually make that work because you're able to write the more performant parts of code in like a compiled language rather than JavaScript and then use it inside of JavaScript. So very efficient and fast for those kind of use cases. It's also polyglot, so pretty much any language can compile to WebAssembly, particularly for the browser, and that's very useful because you don't have to change your language stack to be able to write something in WebAssembly, or write something that compiles to WebAssembly is the more accurate way to say it. It's also portable, because once again, the web, you can't have something that says, oh, I work only on Linux, or I work only on Windows. It has to work everywhere, and so it's portable. Now, if we pause for a second and think about these 5 things, these are almost the exact list of things we want in server-side code. So we want it open, right? The reason the CNCF exists is because we wanted to have an open place to have Kubernetes. The reason the Linux Foundation exists is so we have an organization that can keep this thing open and managed by standards. And so WebAssembly has that same benefit. Once again, we're also looking for safe and secure. Containers got us a lot further along the line of keeping things where they're supposed to be and not being able to break them out, but it's still not perfect. WebAssembly takes that a step further. But then we start to get into the ones that are really, really interesting for server-side. It's very efficient and fast. We want things that run really small, can get around to different places, and can run as tiny as possible. And the polyglot, I mean, that applies to anything, not just the browser, but also that it's portable. It can run on any operating system, which is incredibly useful. WebAssembly is one of those things that gets us much closer to the write once, run anywhere dream that we've been looking at, ever since we started trying to do things like J2EE and all that kind of stuff. We've learned a lot since then as technologists, and have made it a lot more, taken a lot of those lessons to make it so you can actually take these and run them anywhere you want to. So that's a little overview about WebAssembly, why it started in the web, why it's good now, but let's talk about, well, what can it be used for then? The first big category is the general server-side computing use case. This is microservices, functions as a service. It also is very, very interesting as runtime optimization. If you want to optimize your code, and I'm talking beyond the LLVM level, which you can do with WebAssembly in pretty much any language, but if you want to decide how it's going to be optimized, you have to build it very specifically for a specific platform at compile time. WebAssembly is not like that. You can decide at runtime, for example, which runtime you're going to use, how you're going to actually do the compile pass. Are you going to do an AOT compilation? Are you going to do interpreted? Are you going to do JIT? All of that can be determined at runtime based on your device needs and the runtime characteristics you need for your actual code. So it's very, very useful for general server-side computing in that sense. It also is for constrained devices, which I'm going to very loosely put the edge, because the edge means nothing now, as we all know. It's just people like, I run on the edge. What does that mean? Oh, I run on a Raspberry Pi in my basement. And now that also falls into the edge, but when you start thinking about how, and I'll talk more about this kind of relationship, but where Kubernetes can reach to and where containers are best at, when you get to constrained devices or devices that are way out there towards the customer, think cell towers, power compute compute that's at power stations, those kind of things. That's the edge. It's stuff that's way out there. It also includes things like CDN. So it's very useful for those situations. It's also a good plug-in system. And I'll talk about this too, and more in a little bit, but I personally think that that WebAssembly has the potential to be the plug-in system to end all plug-in systems, because it is a lot better than having, most of us here have probably at least touched HashiCorp's Go plugin thing, where you write a plugin and it uses gRPC, or we use something where it's standard in, standard out, where you're calling a script and it's calling it with specific environment variables and it's expecting a specific output type. Instead of having all those kind of things, you could actually write it in whatever code you want and just plug it into code. And there's things that actually already do that. There's also this idea of using it as a library, and I'm going to show that with an example, a little picture here in a second, but libraries, there's something called the component model that is starting to really crystallize that allows you to swap out different parts of libraries as needed, and I'll explain that in just a second. And then, of course, it's great in the browser. So those are some the big use cases I just wanted to list out so people could get an idea of where you use WebAssembly. Now, as for this component model thing, I'd like to use this with Lego blocks. And Lynn Clark, who's a big contributor in the WebAssembly community, she's been around for a long time, she drew these up, and there's a really, really nice way to explain this. So with the component model, everything starts getting defined as an interface. And so this isn't just like an API boundary, it's saying like, here are the things I expect, and you can import that contract and use it, or you can export it. And so what you end up with is, let's say you have, like in this example, a tracing library that needs to use some sort of like URL library and a proxy, and then you have an auth service that has that same thing. So if you work at a big company, you probably have a huge like HTTP proxy thing set up, at least a lot of the big companies I've worked at. And let's say you're on Kubernetes or something and you're using Envoy or using any of those kind of like service mesh kind of things. Instead of having to have specific libraries that you then compile in so it uses that stuff, what you can do is swap out at runtime like a Lego block. Oh, I need the one for my big company, click. So this person using the open tracing one could actually use it inside a big company just by clicking in that little Lego brick. Now, I'm not going to go deep into that. My coworker Brooks and I, who's actually here, we're going to be giving a talk that mentions a little bit more about that concretely tomorrow, but I just wanted to bring it up that that's something that's really, really cool about WebAssembly right now. Now, what are the pain points? Thank you, Gordon Ramsay, first off. But the first thing is networking is still difficult, especially on server side. We're just getting socket support in, and it's going to be landing very soon, but like it's a little bit difficult to do networking at like the raw WebAssembly level. And also, things are very much in the fast-moving stage, just like things were at the beginning of Kubernetes or Docker or any technology trend. We're in that phase where things are breaking and evolving very, very quickly. So if you're not tolerant to that risk, then that's something that could be a big pain point for you. It's also slower than like native code, as in execution speed. So no matter what you do, you're not going to get the exact same performance. But for people who are running things in Kubernetes, that level of performance doesn't really matter because you have a network layer in between it, right? Like between you getting something there and coming back, that doesn't matter too much. But if like really, really like low-level performant code is a need, there's still some work to be done there with WebAssembly. And I don't know how far we can eventually get that. I'm not as good at that low-level stuff. The other thing, especially for server side, is tool chains really aren't there in some languages. I'll just be blunt right now. Java, like true Java without smoke and mirrors and special libraries and hacks, probably a while out. But a lot of other things like Python, Lua, interpreted languages are getting support right now for it. So that's just one of those things. There's some languages that don't really compile very well to WebAssembly that can be run on a server. So those are the pain points there. Now, I mentioned Wasm Cloud at the beginning. Wasm Cloud is a project that I work on. It's entirely open source. It's in the CNCF. And the question here is like, well, if WebAssembly is so good, what do we need Wasm Cloud for? Or any other thing like that? Well, there's this conversation, what is a runtime versus an application runtime? A runtime in this case is, think more along the lines of like a Docker type of thing. Docker is a runtime. It doesn't let you, you're not building applications on top of it per se, it just runs code that you have put into a container image of some kind. That is all that Docker is doing. It's a runtime level thing. Application runtime is something that can actually run an application at scale, do it between different things. And what Wasm Cloud really focuses on is distributed capability-driven development. So those those components thing that I was mentioning before, we do that at a distributed level and not just at a code level and plugging it together. So that's a little bit about Wasm Cloud. So to explain what that actually looks like, we're going to start with a basic demo right here. And we'll go ahead and show, I'll just go ahead and show this. So I've already spun up what is called, this is what we call the washboard. It's the Wasm Cloud dashboard. And this is just the simple thing showing, I'm going to run a simple demo, and a simple demo application. This demo application is going to be at the heart of every other demo I'm doing today, but I want to show you how it works first. So this is a KV counter. The whole purpose of the KV counter is to take a request, and it'll take the path and use it basically as the key, and then it'll increment a counter in a key value store every single time you hit that URL. Now, the nice thing about this code is we can come in and look at this code that we have for the example, and I'm going to just point out, this is Rust for those who are curious, but like it doesn't really matter. We're not doing anything complicated, and hopefully the internet's going to work. If not, luckily I have the backup because, like I said, angered the demo gods if I didn't do the blood sacrifice. So the thing that happens with most code nowadays, if you're doing a project, like think Kubernetes, since we're Kubernetes Community Day. I take a project and I say, okay, I'm going to build like my cat blog. What do I need to do my cat blog? Okay, I need an HTTP server. So I go copy paste that exact same 10 lines of Go server code that I have done for a bajillion years, and I copy paste it in my new project. And then I say, okay, well, which database am I using? Well, I want to use like Redis, or maybe we're in Amazon. I'm going to use Amazon. You have to put it all together, then you build it. Then you have to define your Docker file. And then once you built your Docker file, okay, am I using Helm? Am I using Customize? Am I using Scaffold? Like, what am I doing? And then you have to put that together, and then you have to deploy it. It's very, very long, like, to put that all together, when all you're trying to do is just write like a simple, like, cat blog, right? It's create, read, update, delete, and that's all you have to do. And so what you'll notice in this code, like I said, you don't even have to know Rust to really understand this code, is you have this thing that says, hey, I'm an HTTP server. I don't care what HTTP server is giving me these requests. Oh yeah, sorry, let me zoom. Ta-da. So this just says, I'm going to take an HTTP request and do something with it. And then down here we say, okay, I'm going to increment a counter. You'll notice there's no connection strings, there's nothing in there. It just says, hey, I'm going to send this key value thing and increment it. That's all the code is. So in total, we have 49 lines of code to do all of this. Most of the time you try to do this in any language, you're going to be at least 100 lines of code as you have your server set up, your configuration values, all the different things. This code is exactly like this everywhere it goes. It's compiled to WebAssembly and then can run on any operating system. And so when we come back to this dashboard, we'll see that's the code that's running right here. Now, we've also started something that we call them providers because they actually provide the functionality. We've provided something that can satisfy the HTTP server contract, and I'll plus this up for people. And then something that can satisfy the key value contract. I'm just going to use Redis for this one, but you can use any number of things for this. And then to put them together, all I have to do is at runtime I say, okay, I'm going to link my KV counter with an HTTP server, and I'm going to say this is, and I'm going to set an address, if I can spell address right, to 0.0.0 8080. Okay, so this is just going to listen on an 8080 port. So all the configuration is now handled when you link it together. And of course, there we go. Run that. So now it's running it's now running a server for me. But I also need to give it the key value store that it needs. So I'm going to do the same thing here. And I'm going to say KV counter, Redis key value store. And then I'm actually not going to provide any values because it'll default to localhost. And I just have a Redis server running locally. We'll show you how this actually looks when you have a Redis server running somewhere else in a second. Okay, so now this is all connected up and ready to go, and I can come over here to localhost 8080, and you'll see that there's a counter. And I'm refreshing it, and it can update and do all those things. So this code didn't need to know what database it was talking to. It didn't need to know any of those types of little pieces of information. And why is this important for me? Well, number one, updates. Think about what happens with like a log4j, right? Log4j happens, and we all write bugs. Let's be clear here. If you haven't written a big bug in your life, please let me know. I'd like to know how you manage that. But most of us, we've always written some sort of big bug, so there's always security updates. When that happened, we've talked to multiple people about this. They end up redeploying like 10,000 applications, rebuilding and then redeploying. In this situation, all you do is update the provider and swap out the provider, and you're done. And so that's a really, really powerful feature of what being able to do this distributed does for you. We even did it for ourselves. We started writing something. So our entire Cosmonic platform is written on top of Wasm Cloud. And we started writing things out. We're storing some data in Redis. And then we're like, well, some of this is secret data. We need to make sure we actually store it in a secret place. We implemented this key value contract for Vault, as in HashiCorp Vault, and then just swapped it out without even needing to change our code. And poof, we had security things in place. No change to code. So that's just the simple demo. We're going to show some more complex stuff down the line. But I want to talk about the conversation why most of you probably hear, well, what about Wasm and Kubernetes? And that's where I'm going to really show some cool stuff. But let's bust some myths first here. To answer the question, is WASM going to kill containers? The answer is no. I'm not sure, you've probably seen that debate. I mean, I'm sure it's popular on Twitter. I'm sure it's popular wherever. It's not going to kill containers. There are certain types of applications that just, like, no one's going to go rewrite Redis to not run it, like, to run in web. It's just not worth the effort right now. That works great in a container. There's multiple, like, just think about any of those big applications that have been around for a while. Those aren't going to go to WebAssembly anytime soon. They play along with each other. Things are evolutionary. And I'll mention that a little bit more when we bust some of these other myths. The first one is, hey, I should just run some WASM in my containers. That's a very common one, like, oh, I just want some Kates in my WASM. The problem is you lose a lot of the advantages of having that. Like, you already have the sandboxing, everything you need, and being able to run cross-platform, and then you end up taking it and putting it inside of a Docker container that can probably only run in Linux or something that's shimmed for Linux. And you have the overhead of starting up the Docker containers and the overhead of starting up the WebAssembly. It's not worth it. And I'm going to mention some other stuff that actually uses this stuff right now as, like, basically a Docker replacement. But yeah, you don't generally, it doesn't mean you shouldn't, it just means, like, that shouldn't be the first thing, like, you think of, like, oh, that's how I'm going to use WASM for real. It's fine to play around with, it's fine for specific situations, but just, it's not like it's adding an extra layer you don't need. And then the last thing here is that, oh, WASM and Kubernetes are in and, like, the various runtimes of WASM are in competition with each other. Also a big no. This is all a better together story, and I'm going to show that very clearly in my next demo. But everything's evolutionary. Just because we came up with virtual machines doesn't mean we don't have the need for physical hardware. Just because we came up with containers doesn't mean we don't need to worry about or use VMs, and so on and so on and so on. So WebAssembly is just another evolution. Just because we have WebAssembly doesn't mean there's now no longer a need for containers or Kubernetes. It just means there is an evolution where it can be used for certain types of tasks better than others. So what can you do right now with Kubernetes and WASM? First off is the wonderful Run WASI project. That was started by some people at Microsoft and then a couple other people in the community. And this essentially allows you to run, like, the container shim inside of Kubernetes using a WebAssembly runtime. Like I said, that's the better option than trying to run your Kubernetes, running your WASM in, like, a container inside of Kubernetes. This actually runs WebAssembly directly, just like it would be running a container if you spun up a container in a pod. So highly recommend checking out that project. That's one way you can do it. Also, service meshes, anybody? If you didn't know, things like Envoy and other service meshes already have the ability to write plugins using WebAssembly. So it goes back to that plugin model I talked about, and so you can actually write custom filtering and other plugin models using something that's compiled to WebAssembly. And then you can also use WASM Cloud, which is what I will be showing in just a little bit. So here's the opposite side, and I know this talk is meant to provoke discussion, so some people might vehemently disagree with me here. We have plenty of hallway track space to talk after, and I do want to talk. So one of the things is that it runs smaller. If you really think about it, the default pod limit is 110. Let's just say that your crazy, complicated environment has a bajillion sidecars, and there's actually 5 containers in each of those pods. That's 550 containers that a single node can run in Kubernetes. Now, I know that's oversimplifying it. There's things you can tweak. There's stuff you can increase. I know. But just from, like, the basic, I'm running this at default, there's a limit there. But then also, you get, with WebAssembly, a lot more in that. Pretty much any WebAssembly application runtime right now can run thousands of WebAssembly modules, if not tens of thousands, on a single node, depending on the node size. On this laptop, I think I've maxed out around 3,000 or 4,000 or 5,000, somewhere around there. Just a normal Mac laptop. So it runs a lot smaller, and that's just really helpful. We've talked to several Fortune 100 companies about this stuff, and their Kubernetes server utilization sits around 25 to 35% of their total capacity. And there's some that it's so bad they've actually spun down their internal Kubernetes teams that were running it just because it's so expensive. And so WebAssembly allows you to pack a lot more into a smaller space and get better utilization out of it. It's also entirely sandboxed. Containers are pretty tight, but there's a lot of, like, little security nuances and things. By default, a WebAssembly module can do nothing unless you grant it the privilege to do so. It's also cross-platform, And what I mean by this is we've been telling ourselves a lie for years. Docker is not cross-platform. It is, but it isn't. Windows containers look entirely different from Linux containers. And I knew a lot of those people when I worked at Microsoft. They do amazing work. It's not a knock on that work, but you have to have one for Windows, you have to have one, and on Mac you're just running a VM, and on Linux you're actually running a Docker container, but if you're running an ARM processor, well then you need a different Docker. That's not cross-platform. WebAssembly is cross-platform and does that a lot better. And as people you start getting things, like the Graviton processors from AWS, and people are building their own silicon, and there's all these different things that are going on, you're getting a lot more heterogeneous environments. And that becomes more and more critical to have something that can run everywhere really easily. Once again, I'm going to bring up the edge. I'll take questions at the end. Yeah, I'm saying. So the edge is the other big thing here, is this question of like, well, where can I run it? Most people you talk to know, I'm going to first call out as a huge positive, K3S is a wonderful project. I'm guessing a large chunk of people in here, including myself, run that in our own home labs or our own. We all do that. It's an amazing piece of software. But the thing is you can only go so far to the edge. A lot of those types of companies that we've talked to, like the power companies and cellular companies, it's really hard. Kubernetes likes to be in the same cluster, in the same region, across availability zones. That's what it's good at. It's not really good at pushing out where you have either sporadic connectivity issues or whatever it might be. And so moving out to the edge, WebAssembly allows you to get to that edge a lot easier. And the other thing here is this lower bound problem. I kind of invented this term. Don't try to use it for real, because then I'm afraid people are going to be like, where did that term come from? And I don't want it to be me. But this is a combination of the idea of a cold start versus just where you have to run things. It takes a little bit for things to spin up inside of Kubernetes, even if you have the image cached. So not only do you have the cold start time, it's getting it close enough to your customers to avoid the perception of being slow, even if it's not actually slow. And so WebAssembly has a lot quicker startup, and because it's smaller, it's easier to download and get started when things are going. And you don't necessarily have to keep things like hot containers up. So it's just these are just a couple things that I wanted to mention that WebAssembly does better than Kubernetes, but the thing is they still play well together. So just one little thing to finish off before we go into the next demo is a possible view of the future. And to be clear about this is not the actual future, this is the future according to Taylor. So I could be 100% wrong on all of these, but I'm just going to put a few predictions out there to get people thinking about it, and whether or not this could be true or no, that's totally dumb. Taylor, just shut up, you're wrong. Either one of those is an okay response to any of these, but the first off is I personally think all functions as a service platforms will become WebAssembly based. You don't have to worry about, like I said, the hot container thing where you have to have a hot container that can run certain stuff. You don't have to worry about getting those containers close to the users so that it's fast enough for them. And WebAssembly is just going to, because of the polyglot nature, you don't have to okay, well, yay, we've added support for Rust functions, and yay, now we've added support for X language functions. That goes away, it's just whatever WebAssembly supports you can run. So I think that all functions as a service will be that WebAssembly based in the future. I also think that true microservices will become WASM modules instead of containers. What I mean by true microservices is I'm not talking about that lift and shift 20 gigabyte container that you pulled your Java app from and you're running with 16 gigs of memory. That is not a microservice, as much as we like to sometimes call it that in the internal business meetings. I'm talking about, oh, this is my user service, and this is my pictures service, and this is this service. Those kind of things, those isolated units of business logic will become WebAssembly more often than they will become containers in the future. Like I said before, I think that WebAssembly becomes the plug-in model to rule them all, and that component thing I mentioned is kind of the key there. You can have an interface you define, anything can implement the interface, and it can just be dropped in. And then I also think that newer waves of platforms or tools are going to be built directly on top of WebAssembly. Obviously, I'm biased here. Cosmonic is built on top of the awesomeness that WebAssembly provides it, but I think that a lot of new tools will be built directly on top of that layer to really provide some good experiences and things for users. So like I said, could be 100% wrong, and we'll see what happens in a few years, but this is something to maybe start thinking about. What's the future look like? So let's actually see this in action. This is the demo that I'm pretty excited about. So I just want to review. This is what I showed you earlier. I had something running on my laptop. I had a provider that was receiving an HTTP request, a counter actor that was receiving it, and then that was making a request to Redis, in my case, to increment a key value. So let's go ahead and show you what we're actually going to be doing. We're going to start off with this. So I'm going to be showing how this works in Cosmonic, because Cosmonic has a really nice dashboard to look at. Everything you see here today is 100% doable inside of open source, just to be clear. There's not a lot of things like that I'm doing magic that's just specific to Cosmonic. It just is a good way to demonstrate. So we're going to start off. I have a Kubernetes cluster running in DigitalOcean, and I have a Wasm Cloud host that's running inside of Cosmonic. It's hosted by Cosmonic. And I have a little container that I have sitting around that I'm going to show you as if it were an internal service calling, like that you have running inside of Kubernetes. And on this host, it's going to be able to receive an HTTP request, which is those 3 lines on step 1. It's going to get that, send it to the hosted KV counter, that same code that I showed you before, and then that KV counter is going to call a Redis database back inside of Kubernetes. So imagine if you had, like, your service, you already have Redis that you use for all your services inside of Kubernetes, or a good chunk of them, and you have a service that's already consuming something, a bunch of things internally inside of your Kubernetes cluster. And this is saying, I just want to write one little new piece, and I'm going to write it in WebAssembly and run it in Wasm Cloud. So that's this first demo that we're going to show, or the first part of the demo. So what this looks like when we do this for real is, let me go ahead and refresh this. We're going to hope the internet works again, because we all know, cross your fingers. I'm going to get the internet backup ready just in case. Aha! It heard me threatening. Okay, and then over here, you'll see that we have these things labeled as Kubernetes. These are running as pods, in case you want proof that I'm not just faking this. Oh, yep, sorry. We're going to have to. There we go, big enough. You'll see that there are 3 containers running. This is using the Helm chart that we release. I did discover a bug, so I have to release that bug fix. But all I'm doing is 19 lines of a values.yaml file to be able to start this up, and I'm connecting it into this cluster. And I will, there we go. So it's just, like, basically I've just set a few config values and started it up. So this is actually running. There's 3 of these nodes. They're all labeled. And then I have a Cosmonic managed host like I was describing before. So I have this KV counter. And this KV counter is sitting there, and it's connected to a Redis thing that's running and the HTTP server that's running. And so if I come back here, and I'm going to go into my, where did my, of course it didn't. Give me a second. The network decided to shut down my command prompt. And I have to reinstall. This is proof that I am not canning this demo. I am literally installing curl in front of you. Come on, buddy. That'll take just a second because this isn't running inside of this conference center. Okay, so then it should be right there. So while that's happening, I'm going to show you. I have a service in here that I'll demonstrate a little bit later that actually has all the. Anytime there's a service created, or a new, like, basically one of those links is created, it automatically creates a service for it inside of Kubernetes. So, and it's actually, so that's an actor, it's a WebAssembly actor that does that. So I'm just using it by default, the default, like, thing that I have set up, so it's just using the ID of the thing it's connected to. But I'm going to go ahead and say curl, and it's going to call it on port 8080. Okay, so that's incrementing a counter. So that's going, this DigitalOcean cluster is sitting in New York. It is going to something running in US East, and then calling data that's back inside of that cluster, and then sending it back all the way through. So that's just the first one. That's the first simple thing. Now let's go back to this and show you what we're going to change it to now. So we have this. Now we're going to go to this. So I'm going to connect my laptop in, and I'm going to move that code from the thing running in US East down to my laptop, and everything else is still running inside of Kubernetes. So I'll go over here and show how this works. We have a nice little thing that does this for us, but I'm going to, like, basically kill what I was already running, and I'm going to say Cosmo up. This just does it's a shorthand for, and internet issues. Of course, we'll give it a second to try to catch up. Of course it won't. Okay, we wire in everybody. Well, we'll see if not. If not, I have this canned just in case, but okay, well, we'll pull up the can because the internet. So you'll see a similar thing right here, and we have that KV counter right now. And we'll come back to my machine. Sorry for the small text on this one. I can't really increase the video size. And I'm running that Cosmo app. So it's going to put everything in, glue it all together, and then I'm going to have a host running. And when I come back, you'll see that it actually starts up and has the thing running on there. So when we're going to go ahead and take this, we're going to stop the code we were running on the Cosmonic hosted node. I don't know why it keeps going like that. And we're going to start it on my Mac. So once again, same exact code. It gets launched into my thing, and it's started, and it's all connected. You'll see it's all reconnected to it. Everything's working just fine. I did do this from my hotel room, so it was still in Pasadena. And it's entirely unmanaged, so this is all in these things I've connected in. And if I come back into that container, I can curl it, and I can see that that counter is continuing to increment from the same data store. So what we just did was, like I said, move it over in that diagram to what we were doing with this. And let me try one more time since we're here. Nope, not going to happen. So that's what we did. Now we're going to go ahead and move on to the next one, and I'll make this big. So now we're going to change it a little bit. We're going to say, you know what, like, I don't want to use Redis for this one anymore. I'm going to use the built-in key value store that Cosmonic provides. It could be any other key value database, just to be clear. It's just easy to do this one. And then I'm going to go ahead and do that over here. We're going to keep the actor running on the Cosmonic one for now, just because of internet issues. And then I'm going to say, you know what, I'm tired of using this key value store over here now. I'm going to delete it. We'll see if the internet doesn't work here, I might not be able to do it here and have to. Oh yeah, we're down. We down. Let's try slow. Just make sure it's back. I don't think so. Nope, not working. Okay, while we try to figure that out, this is exactly why I come with the backup. I'm going to try one more time. Aha! Instant success. And we'll even try this over here. Maybe we can get it back to normal. Yes, there we go. Thanks, everyone, the internet. Okay, so now that we have internet, we'll give this a second. There you go, popped up just to prove I didn't just do that with smoke and mirrors. And I'm going to go ahead and move it over so we can see the next part of this demo just fine. So I'm going to say, okay, KV counter, I don't want you on here anymore. I'm going to move you over to my Mac OS one. Okay, that's now starting connected. But now I'm going to say, I'm going to just get rid of this key value one. That's now gone, and I'm going to say, okay, I have this built-in key value one. So you'll see, this code is the exact same code. I haven't changed anything in it. And now I've connected it to the key value store that's in Cosmonic. So, review of where we're all sitting. New York is where I'm making the connection from. I'm coming back to, I'm coming over to have the logic that actually handles it be here in conference now wired network instead of Wi-Fi. And then it's going to talk to a database that's running in US East and do all of this. And once again, 0 code changes, 0 architecture changes, nothing had to change at all there. Now we're going to see if my pod is still up. It probably isn't. So we're going to make sure we've, okay, perfect. And you'll have to see me install that again because I can never remember the curl pod. Okay, and here we go. Perfect. Or not. There we go. Okay, curl. Go back and grab that service name one more time. Okay, you'll see that the counter changed. We were at like 14, 15, 16 before, and so that counter changed again. So I just swapped databases like it was nobody's business. There was no migration. I mean, you wouldn't do that for real in a real production thing. Please don't. But you can swap out and change these things out. And so I was just able to completely re-architect my application across 3 different locations in the United States by doing that. So let's go ahead and say, let's just take it one step further. So I'm going to go and show you this one, blow it up for you for a second. We're going to change it a little bit. Now, what if you have a service, an actor, and this could be something that's actually just calling back to a service you're running in Kubernetes. I'm making it an actor just for simplicity. I'm just going to start this echo actor. This is just a simple thing that echoes back the request to you just to show that it works. And we're going to use something we call wormhole. That's the ingress point for Cosmonic. So we're going to come in through Cosmonic and route stuff over to Kubernetes without any extra changing again. But I'm also going to show you how we've built some things to integrate with Kubernetes really easily. So we have this thing called the service supplier that does that automagical creating a link for you. And so if I come here and I say, I can actually use that. I'm just going to run this on Kubernetes too because we can. Okay, so we'll go ahead and start this up. I already linked it with everything. And so now if I go ahead and start the echo actor, I'm going to start it inside of Kubernetes again. Just to show that, there we go, Kubernetes, true, find hosts. So we'll go ahead and start it over here on this one, and it's all created. And then I'm going to say, you know what, I'm going to link this over to the HTTP service. So this is if I was linking it inside so Kubernetes could reach it. I'm going to say address is 8081, create the link. And if I come back over here to this and I say kube control get service, you'll see that it automatically created this port 8081 for me. So basically, it's a constant compatibility with whatever you're running in Kubernetes and then what you can run inside of Wasm Cloud. So we're going to actually delete that. I'm going to change it to the wormhole that I showed you. And we can actually go back and check that in a little bit if you want to and see that it's gone. But I'm going to say, let's link this over to the wormhole. And I'm going to say, create link, and create the wormhole for it. I think I still have some stale state from when we had network issues. Okay, there we go. Perfect. Withered voice. So I'm going to access this. Give it a second. Okay, so what I just did is now I'm getting something from right here on my machine, going to US East, forwarding through to my DigitalOcean cluster in New York. So this is just if I wanted to send something to a service I had running inside of Kubernetes. And you can see just that I'm not making this up. I'm going to pass a query string. You'll see that the query string it echoes back got changed. So this is all set up to be that way. But we can also show the idea of automatic failover. So this idea of having cross-cloud backups and failovers has become more important in recent years, especially in regulated industries like banking. So what I can do is like, let's just simulate. I'm gonna like pretend like, let's say the node went down or Kubernetes had an issue and now this actor is being terminated. And then I'm gonna go ahead and refresh that so it shows everything clear. And so we don't have the echo actor anymore, and I'm gonna say, now we have it running back over on my Mac. If I can actually click buttons. Okay, so it's going to launch that for me, and it might also we might be having networking issues again, but we'll see. Okay, we are. So anyway, the whole idea, you kind of already saw this before. I can move it around and change it and have it come back into my laptop from the internet, talking to Kubernetes. There's all these different things that go along. So to review, we went from basically this locally to being able to distribute it across 3 different nodes and move the app around. So everything stays compatible. This is the idea. We want it to be a bridge to the future. We don't want people to have to like do something different. You can still be doing Kubernetes. You don't have to like just say, no, we have to go wholesale over to WebAssembly. If you want to try it out, you can try it out right now. So some examples of what you could do basic data, image, processing type stuff, just a simple service that you could run over that's kind of isolated. You could also try one small part of a service like I was simulating this time. Build one thing that can compile down to WebAssembly, have the rest of your stuff still running in Kubernetes. You can also, if you're trying something greenfield, do a full like stateful application as well. So with that, I just want to put these up there. This is a link to our landing page on the right, our Slack on the left if you want to come talk about this and try it out. We'd love to see you, see what you're trying to do. And I think for that, we will now go to questions. Plenty.
Thank you. I guess I get to kick off the Q&A session. So, I mean, the demo was cool. Thank you for the talk. Taking aside the advantages of WASM, right, like bin packing, right, sandboxing, and so on and so forth, a lot of the stuff that you were showing, right, like how much of it is just like sugar that's been built by like WASM Cloud and your company, like Cosmo and that kind of stuff, right? Because all of that flexibility around relinking and like parameter passing and so on, I mean, right, like how specific is it to WASM? Like you could conceivably build a similar platform on any tech that exists, right? And have the same nice GUI, ease of use, and so on.
Yes, you could build, so like underlying, we're completely open about our tech stack. Underlying this is NATS, which is another open source one, right? You can use for anything you want. But what is different is that WebAssembly allows us to do this pretty fearlessly across any operating system and architecture. So you can join, like I just joined my MacBook to this and had it work. And yes, you could make it work, but WebAssembly makes a lot of this easier to do because of its portability and its size. So that's the thing. It's just like building any platform. You could build this using another set of technology. What we have in WASM Cloud in particular is a combination of leveraging WebAssembly and building that kind of platform.
So this doesn't have so much to do with WASM Cloud, but it has to do with you know, the future of like, you know, where this could take where WASM can take web development. So still, if you want to build applications on the browser, from what I understand in the past, or from what I understand even with WASM, you still have a single thread that's responsible for rendering in the browser, and that single thread still has to be controlled by JavaScript. So it's not the case that you could now, using WASM, use any language that compiles to WASM to actually control rendering in the browser, allowing you to do the same language for the backend as you do in the front end for an arbitrary language.
Yeah, so the thing with WebAssembly right now is it is single-threaded. There's currently proposals in place to make it multi-threaded and to go further through that. So that can be done, but yes, right now you're talking about one of the specific underlying limitations that does happen, and it definitely does exist, and it's good to call
out. What does debugging or tracing through an application in the WASM world look like?
Yeah, so tracing is not too difficult. I don't have time now just because we're running shorter on time, but we actually do that. We have it built in by default to the WASM Cloud host. Everything gets traced. Every call to these things, you can export it to OTLP type stuff, and it works great. Debugging is a little bit more of an open story, but because it's a common format you're compiling to, I imagine that we'll be able to create a new wave of debugging tools that can then debug something from any other language that is compiling to WebAssembly. That's what I'm hoping for, at least.
Okay, one more question. Nope.
We have a couple over there, yeah.
Do you see a lot of use cases for running untrusted code, like third-party libraries and stuff with WASM?
Yes, that's actually one of the main things, is because you can, all of this code right here that we're running that I was just showing is untrusted code. And that's another thing I guess I didn't point out to his question, is that like, because of the security benefits of WebAssembly, we have a bunch of signing and some really defense in depth stuff that's kind of cool. We'll be talking about, we've talked about before, you can look up some of those, but you're able to run completely untrusted code from anybody on the platform without too much extra hassle, really, in comparison to some of the other ways you'd have to do it.
Awesome. Well, thank you very much.
Thank you, everyone.
And if y'all are interested in edge use cases, hang around. In 10 minutes, we're going to have a talk on Kairos, another edge project for deploying to the edge.
Okay, I've got 2 o'clock. Depending on what you looked at for the schedule, we had an update because the original speaker had some visa or travel issues. But don't worry, because Jacob Payne is here with Spectre Cloud to talk about the original subject, which is Kairos. It's an open source project intended to deal with issues involved with running Kubernetes at edge. I don't want to steal his thunder, but if you're not aware what that's about and you're sitting in the room carryover wondering if this pertains to you, when you run these things at edge, there are unique challenges where often these edge locations don't have trained staff, yet you need to keep your OS and other components updated to prevent security risks. And with that, I'm going to turn it over to Jacob.
All right. Hello, everyone. My name is Jacob. I'm with Spectral Cloud, and I work with a great team of engineers on the Kairos project. I've been in the Kubernetes space for about 3 years now, but most of that has been focused on edge solutions and edge tooling. So today we're going to kind of chat about Kairos, which is an immutable Linux operating system and edge factory. But before we get into that, I kind of want to just go over what is edge. Quick show of hands, how many people here know what edge computing is or have worked with it? Okay, good. Quite a few of you. Wonderful. So edge computing, when we think about it, is the computing, when you think about traditional like DevOps, you're working in data centers, cloud environments, and they solve a lot of problems for you because they have things like redundant power, redundant networking, tons of compute space. Edge computing is computing where these devices tend to be in areas that aren't optimized for computing. They're restaurants, vehicles, telco, all the cell towers, all kinds of locations. So with that brings its own unique challenges, right? You're going to have issues with reliability, a lot more hardware failures, unreliable networking, intermittent connectivity, all kinds of things. And with these edge devices, what we're typically seeing is a lot of sensor data collection, so recording real-time data and then either sending that back to a location or even analyzing it on site. You can also see it in user applications. So you may have a restaurant that their POS system, you want to manage that software, distribute updates. And so when we look at edge and kind of how we approach these problems, great solution for that is Kubernetes. Kubernetes can help with a lot of that kind of responding to environmental changes because you have the reconciliation. It also makes it easy to get up and running in edge environments because a lot of the applications that you're used to are already configured to be deployed with Kubernetes. So it can make it easier to get up and running, and it can also help with some of the scaling concerns because Kubernetes can manage multiple devices, help them coordinate. But with that scale comes its own challenges. So when we talk about edge environments, typically you can have upwards of thousands to tens of thousands of devices. And so you're going to need to manage all of those. You're going to need to provision all that hardware. You're going to need to set it up on site. And you're going to need to make sure you're doing that consistently. So we can't have, in edge computing, you can't have the snowflakes. You can't have where you just shell in and quickly fix that deployment that went sideways, because you may not be able to get a shell and you maybe have to do it 1,000 times. So edge needs to be reproducible, and you can't have any, you really want to avoid any customization per deployment. So the other challenges with the Kubernetes is how do you manage those day 2 operations? How do you manage your application, trigger updates on these sites? Security is another big concern, especially on edge, because it's not only, if you think traditional security in like a cloud environment where you're focused on firewalls and access, API controls and all that. In edge environments, I can walk in and grab a device and throw it in my pocket and then take it home and start scanning the drive. So security gets a little bit more complicated on the edge. You also have limited resources, so form factor and software footprint become important. You can't have, you're not going to have your 2 terabyte of RAM available. You might only have 4, and that's 4 for the OS, Kubernetes, and then whatever's left is for your application. So Need to be cognizant of that. And then the other thing is you're not always going to have technical experts on site to do these deployments. You may have non-technical users doing these deployments, consumers, and also sometimes even getting to these environments. So, you know, some of these are really remote sites, and so if something goes sideways and you need to get just any person on site, that might involve getting a pickup truck and driving, you know, through the desert for a while. So what solutions do we currently have for these problems, right? There's K3s, which is a fantastic Kubernetes distribution. It solves that kind of form factor issue and the software footprint. It's a very compact distribution, but it doesn't do any management related to the operating system. So for that, you could look at something like Talos, Flatcar, Bottle Rocket, but they all have their own issues as well. Talos is very opinionated, so you're not going to be able to do, you know, you're going to have to kind of do things their way, which might be difficult for migrating existing applications. Bottle Rocket cannot run control planes, so that means that you're going to have to, your devices need to be able to call home reliably, or you're going to have to find another solution to deploy your control planes. And then Flatcar is another, it's a great operating system, but you can only configure it through cloud configuration, so that can sometimes be problematic. K3OS, it was a great product, but it's not really being developed at the moment, and then that leads us to Kairos. So Kairos is we'll get into it in a bit more detail, but Kairos gives you the flexibility to kind of control. It's not opinionated as far as what operating systems you're using, and it's not going to box you into a specific set of tools. So it's a lot more flexibility, a lot more customization, while still getting you a lot of those advantages you need in Edge. So when we're evaluating solutions for Edge, what are we looking for? You want immutability. That goes back to the reproducibility across all the environments. I need to be able to simulate in a lab what's going to be simulated in the field easily, and I need as few failure points to that process as possible. Orchestration is a big factor of that because not only are you going to have to manage a lot of deployments, they're not all necessarily rolling out at once. So I've seen some use cases where you have devices, you'll provision them with some initial software from the manufacturer, and then they sit on a shelf for 6 months to 2 years before they're actually deployed to a site, and you don't know what site they're being deployed to. So you need a solid orchestration to be able to manage that and ensure that you're able to get those deployments out. Disk encryption, like we talked about, important for security because hardware is going to be accessible to some extent, so we need to make sure that anything on those devices we're going to be able to secure in the event they're compromised. OS customization is also going to be important. A lot of times we're going to be dealing with, we're going to require custom drivers, or we're going to have special hardware that we're interfacing with. So we really need to be able to modify that operating system. We need declarative configuration that's going to make our change management much easier. And it's going to make it, as we roll out updates and make these changes across all these environments, it's going to make it simple to understand what the differences between environments are. Extensibility is, again, just kind of the ability to add additional, not be boxed into specific set of tools, add whatever, applications or customizations you need, because especially with Edge deployments, you tend to have a lot more of those special cases as far as, disk layouts or all kinds of things. So you need to be able to accommodate that. And then lastly, you also want to consider, how well is it going to integrate with Kubernetes? So, can I manage my building these artifacts, or kind of manage these changes through Kubernetes? And then how am I deploying Kubernetes on top of this operating system? Because setting up Kubernetes from scratch is a bit involved at times. So you want to make sure that whatever tool you're using makes that process as simple and manageable as possible. So with that, let's talk about Kairos. So Kairos, opposed to some other tools, it's a meta distribution. So what that means is Kairos does not have a set package manager. It's not its own OS or Linux distribution. It's actually a layer you can put on top of other distributions. So going back to that customization aspect, like you can just take any Linux distribution Docker image and then use that as a base for Kairos to build out your excuse me, your OS image. So Kairos, layering on top of those Linux distributions, Kairos introduces the immutability. So it's gonna allow you to have an immutable root file system. That's gonna make updates much easier. Installation is gonna be very consistent because you're not installing or making changes on site. Those changes are already just baked into the image. It's also gonna give an agent for interfacing with these changes. So triggering modifications to the environment, triggering installation, all of that's gonna be managed through the Kairos agent. We'll get into more detail about how you interface with it. There's a couple different ways, but Kairos will all manage that at the core. And then most of the Linux distributions in their container images do not include the kernels and the initRD. So Kairos will take care of packaging those in and making sure that you can control that and modify those as needed. So that's kind of like the core functionality of Kairos. There's also a step further where we have Kairos standard. This introduces Kubernetes distribution. So by default it uses K3s, but you can also use CNCF, RK2, whatever, any distribution you want to add. And it also introduces some tooling for automatically orchestrating these devices. So when you want to create a highly available cluster, you don't have to have all of that laid out from the beginning. Devices can actually find each other and coordinate a highly available cluster just by running on the same network. So talking about configuration with Kairos, this is one way to introduce configuration. There's actually a couple we'll talk about, but it's easiest to kind of talk through. So this is cloud configuration. It's standard cloud configuration. You can also use any of the other existing cloud config settings. It doesn't disable it or anything. It's just on top of it. And you can set things like the host name, introduce some users, turn K3s on, and really there's a lot you can do with Kairos. This is a very small snippet of the settings you can control, but you can declaratively define how do you want this device to behave or these devices to behave in your cloud configuration. And then the Kairos agent can just read that configuration and apply it to your device consistently. So let's talk about the immutable OS. The way we manage this is we kind of partition the boot drive in a special way. So we have our active and passive images. So that's going to be your root file system. That's that image you built initially. We'll get into why the active and passive and recovery. And then there's going to be the persistent partition. So that's where all of your application data is actually going, your persistent data is actually going to run. So if you think about like you're running an etcd node, all that etcd data actually needs to be persisted. We can't write to the immutable portion of the OS. So that's going to be, the persistent file system is layered on top of the immutable root. And then we can persist your application data. And then lastly, there is the OEM partition. This is a small, like 100 meg partition. It just contains the Kairos, that declarative configuration, persisted on disk, so that way we know what to do on startup, and you can kind of tweak Kairos that way. So why do we have the active and passive? So the active, passive, and recovery partitions make upgrades really reliable. So when you're coming in, you somehow, as a user, you want to trigger an upgrade from one OS version to another. Kairos agent will then go ahead and download the image from your container registry into the transition image. It's then going to copy active to passive and then transition to active, and then it'll reboot. So what this gets us, on the next boot, you're going to boot into your new active image. So OS updates, because the root file system is immutable, we don't have to wait for any installers to run. We don't have to rely on any registries being up. Everything that you need to run to set up this device is available to you right there. So we're going to boot up into the active partition. Now, let's say you roll out a change and something goes wrong, right? It fails to boot, you rolled it out to the wrong hardware, something like that. Kairos can actually detect these boot failures, and then it'll automatically fall back to the last version that you had. So that's what the passive image is for. So It'll automatically roll back the upgrade back to the passive image, and then you as the operator can kind of decide how you want to go about triggering a new upgrade or managing that. And then it's not depicted here, but there's also a recovery partition. So the recovery partition is the image that was initially used to install Kairos. That doesn't necessarily have to be what you use to run it. It's just one that we reliably know booted at least one time. So we persist it permanently, so that way in the event that both the active and passive fail for some reason, you have a bootable recovery image that can, take a more aggressive recovery by basically resetting the device and reprovisioning it. Obviously that's not ideal, and you want to kind of stick with the active and passive, but in extreme situations that could still save you from having to have an operator go into the field to recover a device. So with this core architecture, this enables us to do a lot of things in Kairos. So for example, like I mentioned, the configuration, you have that declarative configuration, but it doesn't necessarily have to be distributed as cloud configuration. By default, when Kairos starts up, it will generate a configuration. So it's going to generate a pairing token, start up with K3S, and then it'll display a QR code. You can then take that QR code and put it on other devices, and those devices will automatically join and form a cluster with that first device you booted up. Does anyone here do like home labs, running servers at home, anything like that? All right. Super nice for that. I actually use it myself, and it's really great for just because you can get up and going really fast with zero configuration. So the other option too is the web UI. When Kairos boots up, it'll give you, if you have the address of the node you're booting, you can sign into this UI and then enter your cloud configuration there and manipulate the OS right through the UI. And then so there's other ways there's a lot of ways you can do configuration. All of it is going to funnel back through the agent in that OEM directory. But these tools that we have, like the web UI and the QR code, are just built in to kind of help get up and running. Kairos also supports TPM disk encryption. So that can give an extra layer of security by ensuring that the user data is always encrypted. So in the event your device is compromised, they're not going to be able to decrypt any of your application data. You can optionally encrypt the whole OS if you wanted, but for performance reasons, it defaults to only encrypting user data when enabled. This also, in addition to just using TPM, Kairos supports processes where you can actually have remote authorization. So when a node boots up, it doesn't know how to unlock its own disk, and it has to call back to either like a central SaaS platform, or you could have it call to other peers, and it needs to authenticate with them to ensure that it's allowed to get its token from another machine. So that way, if a device is taken out of an environment, there's no way to decrypt it without bringing it back into that environment that you trust. Another one is our peer-to-peer networking. So this is super nice. You can actually start up a bunch of nodes. And if you think about traditionally deploying a Kubernetes cluster, first thing you're going to do is lay out your control plane nodes, get the control plane up, and then just spin up a bunch of workers. Kairos actually supports coordinating all of that for you. So you can just take a bunch of devices, provision them with your configuration and your OS image, and on startup, they'll discover each other on the network, and they are going to use a distributed ledger to actually perform leader election, figure out who's going to be the control plane, who's a member of this cluster, and they can form highly available Kubernetes clusters with etcd and everything with no intervention from the user. So it'll just wait until enough devices are online to go HA, and then it'll just start spinning up, and as new nodes come in, it can automatically join them into the cluster as well. Also, we have Aurora Boot. So this is an iPXE boot tool. You can configure a DHCP server to point to your instance of Aurora Boot. And this will distribute the net booting the operating system as well as a cloud configuration that you set. So if you're running like a virtualized environment and you want to leverage Kairos, you can just have all your VMs start up, connect the DHCP server, will tell them where to go for a boot, and then they'll all just automatically provision themselves with Kairos. And additionally, you could use the peer-to-peer networking, and then they would automatically form clusters as well once they're up and running. Lastly, we can also build these Kairos images. So when we talk about the flexibility of Kairos, when we talk about building an OS, installing your packages, installing all the drivers, all of that is done as a Docker file. So if you want to build a Kairos image, you literally would just pull from Kairos base, and then you can install whatever additional packages you need in your Docker file. It's a standard OCI image that it's produced. You can use Docker build to build it. And then that image can be directly installed onto these devices when they boot with Kairos, or you can use the OS builder, which is a Kubernetes controller, to build other artifacts such as ISOs, netboot artifacts, also cloud images as well if you want to do like AMIs or so on and so forth. So it's really simple to get up and running with Kairos, and it's really simple to generate these artifacts. That's kind of the factory aspect of Kairos, is building, even though it gives you the flexibility to pick whatever distribution you want, whatever Kubernetes you want, we also give you the tools to build those artifacts through Kairos. So it's really simple to get up and running with. So before we jump into a demo of all this, does anybody have any questions about what we've kind of covered so far? Or
I'll just talk loud. I can talk loud too. Thank you, though. So I was wondering, is each edge device a node in a cluster, or is it a cluster by itself?
Itself as a single node cluster, or you can have them, by using that pairing token, you can tell them to form clusters. You can also give nodes different tokens and form multiple clusters on the same network. It's really up to you how you configure it. When we talk about node, it's like a physical device that's going to boot the Linux operating system. And so they're all going to boot Kairos, and then they're going to look at that cloud configuration to figure out how to get Kubernetes set up and what to do with that.
Yeah, I have two questions. Regarding that, the QR code, talking about, I think of like worker nodes, adding worker nodes, and you said with the configuration, so the QR codes, could you add, you had another sensor at a region, then the QR code could add that to the particular node? Or what does, I don't understand what the QR code is to particularly add. What are you adding with the QR code? Okay, great. And you mentioned POC like a restaurant. I could think like food trucks maybe as a use case, but that just doesn't make a lot of sense to me as an edge case. So could you explain that?
Some restaurants, you can think of like the simplest case, which is just the POS system. So the cash register that they're tapping your order in on. You could just provision those with Kairos, but some restaurants are actually getting more advanced with it, and they will have, excuse me, so they'll have all those POS systems. Then all of their equipment will actually have sensors on it trying to predict failures so that they don't have downtime. So like the fryer will have a Linux device running on it and recording, run operation and all that kind of stuff to predict failures. And then some of the really cool ones are doing, like they'll have a camera that watches the drive-through and then uses computer vision to determine how fast orders are going, all of that kind of stuff. So restaurants are getting real complicated with some of their tech. But when you think about these restaurants all across the country, something in, like here in Pasadena, they're probably gonna have a great internet connection and they could just call home to a cloud provider. But restaurants in more rural areas, they may not have reliable internet. They may be using satellite. So that's where you're going to get into the more disconnected cases and where your restaurant manager is going to be the one asked to replace hardware because you don't have engineers on site. I could go on all day about edge use cases with things like that, but Kairos is really trying to solve for that case of I have non-technical users and I have unpredictable environments. How do I make sure that we have a reliable product?
Yeah, I was going to jump in and point out that at KubeCon, I think this was almost 4 or 5 years ago, Chick-fil-A presented, and you'd be surprised how much tech is in fast food places. So the things they do, they all want to track cold chain, like did food ever reach a bad temperature, but they're tracking the fryer temperatures for quality. And a really cool thing they're doing on some of these is many younger people will only order through mobile apps. They'll come to the store to pick things up, but they also have sizable business in the drive-through. And people who are casual, where if they see a long line, they'll go to the next place on the street. And what they are doing is tracking the people with the mobile app coming inbound to the restaurant to pick up their order. When they're a block away, they'll tell them, don't go in the drive-through. We know you're here. Pull into a spot. They have cameras that will learn a person's car and have an employee run hot food out that didn't get delayed 20 minutes while they're in the drive-through. And I'm told that they can generate hundreds of thousands or millions of dollars a year of improved business by just accelerating that customer experience. So all of these places are going tech. In fact, it's too bad Cali Burger across the street is closed, but in prior years, they made burgers with robots. And this is their headquarter show place, but it appears to be closed. But they had robots flipping burgers in there.
Awesome. Yeah, so with that, we can go ahead and we can show you a demo here. So what this setup is, so we're going to be using vCenter with VMs, but we effectively have all these devices are on, think of it as just a flat network infrastructure. One of the devices is running a DHCP server as well as Aurora Boot. That one's already up and running. And then we're going to boot up a couple other devices. These have a blank disk attached to them, and they're just set up to do network boot, but they have no configuration on them. So, hold on, I'm going to try to find my cursor here so I can scrub. This is to run the Aurora Boot server. As you can see, it's just a Docker run of an image. You pass in the configuration. This configuration is going to say, here is my Docker image that has my operating system on it, as well as some basic cloud config. So there's that join token we talked about. We're going to enable K3S, those kinds of things. We can see here in the logs of the Aurora boot, it's started up, it found its ISO, and it's ready to boot things. We're going to go ahead and start up those VMs. You can now see there's some activity of devices. They hit the DHCP server, ask where the boot server is, it points into Aurora boot, and then they're going to start downloading the kernel and the initRD to boot. This here is a terminal of one of those nodes being provisioned. So it has, you can see these are just dmessage logs, systemd is starting up. And now it's going to start getting into Kairos. And Kairos is going to, because our cloud configuration told it to automatically provision on the first disk that meets our parameters, it's going to begin provisioning and installing right away. So no intervention from the user. We just started the machine up on the network, and now it's already installing the OS so that it can boot independently. It's going to take a second here to copy all of that, and then we also have a couple of them running. You can see all of these are doing the installation automatically, no intervention. We're just opening the terminals to look at them. At this point, it looks like they're wrapping up the installation. They're saving their configuration to the OEM directory. They're going to continue finishing up the installation. All right, there we go. And so now they're going to start rebooting. At this point, they're booting from their own boot disk. You can see in the grub menu there, we have Kairos fallback, so that's that passive image, and then recovery. There's also some other nice ones in there. And then once these devices boot, they're now fully configured, and they're going to try to form a cluster. So once enough of them are up and running, we're going to go ahead and shell into one of them. And then through the Kairos agent, once we connect to it, we can ask the Kairos agent for the kube config for our cluster. So here we are SSHing into one of those nodes we just provisioned, and part of our cloud config was our own SSH key, so there's nothing to set up. We then can ask Kairos for the kube config for this cluster. Kairos then returns it, and then we're going to go ahead and download that and connect to it with K9s. And then without any intervention from us, you can see that we now have a multi-node, highly available cluster with 3 nodes of etcd, 2 workers, automatically provisioned. This is trying to leverage as many of the features as you want, but you could also do this installation with a USB stick, get these devices up, and then power them on later on the network. If you're buying bulk hardware, you could have your OEM manufacturer pre-provision the installed image, and then when they get on site, they can figure out what cluster to join in from there. Or you could have some basic user intervention where they enter, whatever information. Really, that's the advantage of Kairos, is it's highly configurable. So it's not opinionated about how to use Kairos. So all of these, everything funnels through the agent, but the agent's really flexible with how you use it. So with that, big things with Kairos are the immutable OS. It makes it reliable. It makes it consistent and reproducible. The OSs are distributed as container images, so it makes it easy to leverage existing container infrastructure that you have up and running, as well as easy way to package it. It's nothing proprietary. It's just a standard OCI image. We simplified Kubernetes provisioning and the OS lifecycle management, so those aren't 2 different pieces that you have to figure out how to manage. They're just joined together. P2P network for automatically kind of discovering and managing, discovering and coordinating deployments. These HA clusters, and then the cloud init and the declarative configuration makes it easy to roll these changes out and know what's being deployed in these sites. And then, of course, you can keep your OS, whatever Linux distro you're comfortable with or you're already running on. You can bring it into Kairos and just get up and running with that, so you don't have to try to migrate your OS in order to adopt Kairos. Kairos will just layer on top this functionality. And then if you want to take it a step further, Spectral Cloud offers Palette, which is our multi-cluster management platform. Palette is integrated with Kairos, so if you want, you could manage all of those clusters that are being provisioned. They can automatically connect back to Palette, and so you have a central management hub for distributing these upgrades. We also have pre-configured packages for Kairos clusters and how you want to set them up. And you can deploy with our packs, you can actually deploy your applications within the platform to manage all of these edge sites. So it's really great, because with one click, you can just go ahead and update thousands of clusters, and that's all it takes. So if you want to learn more about Kairos, please check us out on the Spectral Cloud community Slack in the Kairos channel. We also do office hours. You'll occasionally find me in there. If not, then someone else on the team. There's Matrix, and then if you want to get started with Kairos, go ahead and check us out on our GitHub org, Kairos-IO. You'll find all of these tools that I've mentioned in here to try them out. So if there's any other questions about Kairos or anything, I'm happy to take them. Oh, sure.
And if you have some, I'll hold the mic up to you after, but I just want to make it clear, you say this is open to choosing whatever Linux OS I want, the Red Hat flavor, the Ubuntu flavor, Debian, whatever. And how about Kubernetes? Is that open as well, where I could choose K3S or Microshift or any of the others out there are all doable?
Yeah, absolutely. We have, I know we have K3S, CNCF, and RK2 packaged today, but the packaging is very simple, and you can easily introduce other providers if you wanted. Or if you want, you're welcome to make a feature request on the Kairos org.
And I'm curious about this technique of passing it into an OCI, packaging it in an OCI container. I take it that I'd want to stand up my own container image registry if I didn't want to host this out on the public internet. And is that a typical element of an edge use case for these, of running some image registry?
You can run your own private registry, or if you don't have anything sensitive in your OS, there's nothing wrong with just pushing it straight to Docker Hub. Kairos actually publishes to Quay. That's where all of our base images and standard tooling is published right now. So now, if you had your cloud config where you had it, calling home to your own platform, or you wanted some proprietary, you would use your own registry. But if you don't have anything sensitive in there, you wanted to just provision a standard installer that then calls out to get that sensitive information, there's nothing stopping you from putting that on.
I think typically, though, at Edge, I've heard stories of people who use Docker Hub where they have throttling if you don't have a paid account. And then there are people who need to support recovery air-gapped. So in other words, the store loses power, comes back up, but maybe the internet connection isn't up yet after a power loss because it depends on external entities. So that locally hosting this, especially if you're also bandwidth challenged, locally hosting a caching registry might not be a bad idea.
Yeah, no, I definitely, most people I've seen using Kairos have their own registry, but it's not a requirement. It's standard OCI, but yeah, definitely if you have air gap or throttling concerns.
Where does that fit in if I use that Aurora iPXE server that you showed there in one of the slides? Is it also keeping full images in some way, or does it, in the iPXE boot up, point to an image registry to bootstrap this thing up from an empty system?
Yeah, so what's really fun with Kairos is because of how easy it is for us to do upgrades and transition, your installer can actually be an entirely different OS from what you want to run for your application. So actually, if you use Palette, we have a generic installer that everyone uses, and all it runs is our agent to call back to Palette to figure out what image you actually want to run. And so what you can do with the Aurora is you could just boot a standard Kairos generic public image, and then in your cloud config, you can declare your private image from the private registry that you want to actually do the installation with, and so it'll boot with the public one, and then it'll download your private one and install that.
You know, you seeded a thought in my mind when you talked about kind of a bifurcated OS where you start with one, use another, but is it possible to use this to install a hypervisor layer so that you would actually use this edge node to run a hypervisor and maybe even multiple virtual nodes?
Yeah, absolutely, and that's something we've seen some customers doing, is they'll provision Kairos, and part of their image, it'll have all the libbird packages installed and ready to go. They then use it to get a basic Kubernetes control plane up, and then they can use KubeVirt as the hypervisor to provision VMs. And then within that, all those VMs being provisioned can then use Aurora Boot that they pre-provisioned. So yeah, you can really, the nice part about Kairos is those very early operations with provisioning, the OS management, the network booting. Kairos can handle all of that. So you can start with Kairos and carry it all the way up to your day 2 operations where you're running your applications.
Does day 2 still involve that iPXE server, or at that point is that out of the picture? In other words, is that a one-time use on first day, or is it involved on day 2?
It depends what you're doing. So if your devices typically aren't changing what OS they're running, then I wouldn't consider it a day 2, but excuse me. We have some users where they're actually reusing hardware for all kinds of different use cases. So they'll provision it with one OS, use it for a month on a site, and then they wipe it. So they'll reset it, and then they'll put it in a different environment, and then it needs to re-provision with an OS. So it kind of depends customer to customer, but you can use it either way, whatever.
And for a brand new device that just came from the factory, maybe through a distribution chain, I know that LF Edge, the Linux Foundation group that manages Edge, has their secure device onboard project that works in conjunction with FIDO, but it's designed to take empty hardware and imprint it at a site where the only people you have at that site are somebody capable of plugging in the network cable, the power, and no other knowledge, not even login credentials, and it just takes off. Does that work with this?
Yeah, so that's actually, so in that case you would use like the generic install, you would give the OEM a generic installer for this. So, you know, that's actually one of the use cases we do with the palette management platform,
Mm-hmm.
but you can do it yourself if you wanted. And so they use the generic installer, and then the OEM manufacturer will give a list of TPM hashes of here's all the hardware we provisioned for you, and it's sitting in a warehouse. So you don't know what site that device is going to be deployed into, but all you have to do is have someone working on site plug it in. It'll then boot on the network, find the other Kairos devices, and know, okay, I'm on this site. Let me call home to get my provisioning instructions. And then it'll, the platform, the SaaS palette can then do a challenge on the TPM to say, what is your TPM hash? And then if it's in a registry of known devices, it can automatically be provisioned. So that's how you can kind of have that disconnected where
So, sorry for monopolizing the mic, but does anybody else have questions for Jacob?
Yeah, so just following up on the question I asked about topologies that you see on the edge, could you walk through an example topology? Like, is the truck, say it's Pepsi or something, they have the central location where maybe the central cluster is running, and they have these satellites, and then they have the trucks. Is that like each of them is a cluster, or what's a typical topology you see in the wild? Mm-hmm. Okay, cool. Thank you.
I had one more. Does this support x86 and ARM processors, or is it flexible enough to go beyond the x86?
Yeah, absolutely. So when we talk about different architectures, the challenge there is not really with Kairos, because when we talk about those images being written to the disk partitions, it's, as far as Kairos is concerned, it's just bytes. It doesn't do any execution. It's not trying to run anything. So as long as the Kairos agent is built for your architecture, you can run Kairos on it. And Kairos is all pure Go, so we have it cross-compiled for ARM, x86, and all of that. You can run into some challenges with specific hardware, like Raspberry Pis, for example. They don't have BIOS, so you have to kind of configure the firmware. So for that, we have some additional tooling that gets loaded when you're provisioning for those specific devices. But it's not out of band of how Kairos functions. It's just that we know that during the installation, and there's actually hooks for all these different phases. So on Raspberry Pi, you have a after install hook to configure that firmware to load grub so that you can still have all the fallback and such.
Anything else? Otherwise, I'll remind you that, well, let's start by first recognizing that this is a community conference. We have people who volunteer to give talks like that. If you, like me, think that Jacob gave a great talk, why don't we get together and give him a round of applause? So this SCaLE conference is community driven and it's rather unusual, and we have some events that you don't typically find at kind of the corporate commercial conferences, including social events. I'd encourage you to join those. This evening we have the Upscale Lightning Talks, which is fun and social, and I believe they'll have drinks available there during that event that I think is at 6:30. We do have one schedule change, that in the printed schedule we had a speaker who couldn't be here at 5:30 in this room, but we're substituting in a birds of a feather on home labs, and this could be home labs in general involving Kubernetes or not. And I intend to be here for that. I run a home lab and have given talks on home labs, but and home lab really is the ultimate edge when you think about it, when you're hosting your own things in your home rather than consuming things off the internet. There's actually a lot of cool stuff available. It turns out you can run your own equivalent for privacy, availability, equivalent to things you'd get out of Google Docs or Office 365. You can host your own photograph repositories, media, music. So if that at all interests you, show up here in this room at 5:30. The other unusual thing is if you're local to the area and maybe have family, one thing that often surprises people is on Saturday we have what's called the Next Generation tracks. These are for people under age 18. So we have a whole track which is speakers under age 18, and we have workshops and talks to help educate the next generation of people moving into tech. So if you weren't already aware of that, I'd encourage you to spread word and take advantage of that. And you'll likely, some people are shocked when they come here on the weekend and see a lot of little kids running around, because that isn't a normal characteristic of most tech conferences, but it is here at SCaLE. So thanks everybody for coming, and I hope you enjoyed this, and there's plenty more, 2 more days plus the rest of today. So, thanks.
that approach in terms of cost and operational complexity versus two other approaches that are commonly used, that are less right-sized or not right-sized. We'll compare the approach on three public cloud Kubernetes clusters, Oracle Cloud OKE clusters, Google Cloud GKE clusters, and Amazon Web Services EKS clusters. And we'll look at two kinds of ARM compute. We'll look at Ampere A1 ARM compute on the Oracle Cloud and on the Google Cloud, and we'll look at Graviton ARM compute on the AWS Cloud. So here's the remainder of the talk. We're starting to launch into a little bit more details about the right-sizing approach in terms of the right-sizing the inference resources and right-sizing the compute type. Then we'll look at the experimental setup that we use to evaluate that approach versus two other approaches. We'll look at the results using that methodology, and then we'll summarize and talk about one more thing. Okay, so with respect to right-sizing the inference resources, as I said, we're using the Aloda Luna Smart Node Provisioner to add and remove compute nodes. Aloda will add nodes to the cluster for pending placements using its bin packing versus bin selection policy. So it uses bin packing for pods with smaller resource needs so that they can be grouped together on the same node. And it uses bin selection for pods that either have larger resource needs or that have special needs, like GPUs, for example. So this is kind of a diagram showing those two modes of operation. Now, this Luna Smart Node Provisioner is suitable for any kind of bursty loads that run on cloud Kubernetes. So we've previously talked about using Luna to actually manage x86 plus GPU nodes, they're expensive nodes, for DL training. You know, today we're talking about serving. And so we used Luna to validate DL, AutoML, running on Ray, Tune for tabular and text classification data sets, and we got very good results for reducing the costs on training. So adapting Luna to work on serving was pretty easy. What we did is we changed the bin packing versus bin selection policy to favor the fact that these cloud vendors have very granular size ARM instances, which can be very cost effective. We turned on the Luna option that said, you know, consider using ARM as well as x86, whichever's cheaper. So we had, you know, multi-architecture set up so they could choose either one. And finally, we actually made an multi-architecture version of Luna itself so that you could create an all ARM cluster if you wanted to, if that's more cost efficient for you. With respect to using not only the right-sized instances, but using these ARM CPU instances, let me just step back and say the latest ML Commons benchmark for data center inferencing does show GPUs delivering the most performance in an absolute sense. But your mileage may vary. If you are doing low latency, small batch size, you know, cloud server scenarios like you would for something that's, you know, delivering an ETA to an app, it can run more cost efficiently on a CPU, so it's worth evaluating. And so we did pre-deployment tests for our workload and figured out that it would work fine on a CPU-only setup. And so for the right size runs, we just did not request a GPU for the pods we were placing. We requested CPU only, and then Luna chose the ARM CPU as being less expensive than the x86 CPU on all three of these clouds for the size pods we were requesting. And as I said earlier, we are using this right-sizing inference on two kinds of ARM compute. On the Ampere A1, which comes with an Ampere optimized AI library, this is tuned for CPU DL inferencing, so that's one of their key use cases. And also the Graviton, which is available from AWS, is intended for best price performance on a variety of workloads, including DL inferencing. So let's talk about the setup we used for this evaluation, and then we'll, once you see the setup, then we'll show applying that setup to the three different cloud vendors. So we wanted to choose a tunable DL inferencing system that was deployable on cloud and that included auto-scaling. So for this purpose, we chose TorchServe. TorchServe is a high-performance, full-featured open-source tool for serving PyTorch models. And it supports setting resource settings for specific model pods, model serving pods. TorchServe supports deploying on cloud Kubernetes clusters. And in fact, this picture right here is of the deployment description on AWS. And finally, TorchServe includes a load-triggered autoscaler, which is based on Kubernetes horizontal pod autoscaler. And so it changes the number of DL, serving instances behind a load balancing endpoint depending on the load that's presented. So this is kind of the ideal setup for us to do this evaluation. We wanted to choose two models that had different resource requirements so that we could show the importance of right-sizing the nodes that you select for the models sizes that you have. So here's two different models. They both do image processing. The VGG16 model has 138 million parameters. So it's quite a bit bigger than the SqueezeNet model, which has 1.2 million parameters. We wanted to allow TorchServe to scale separately for the two kinds of models. So we basically, inside of our Kubernetes cluster, which you see right here, located in the cloud, we actually did two deployments of TorchServe, one for VGG16 and one for SqueezeNet. We did this because we wanted the worker replica size for each to be suited to the size of the model, and they had two different sizes. And we also wanted the replica count for each to capture the load presented to each model. So you could imagine sometimes VGG16 load was high and SqueezeNet load was low, or vice versa. And so we wanted to kind of tease that out. So we basically did these two deployments. So you see the two deployments there. You see that each one has its own horizontal pod autoscaler. And then you see Luna autoscaler at the bottom that's watching for pending pods that aren't being placed and adding suitable resources to that Kubernetes cluster. And it's also watching for nodes that become idle, and it's removing them from that Kubernetes cluster. For the workload, we used this Hey load generator. We ran 150 parallel threads, and we used it to predict what is the picture here on the bottom right-hand side of the screen. So a kitten. And we tuned TorchServe for low latency, set its worker and netty threads to 1. And we set up the TorchServe horizontal pod autoscaler to have the autoscale trigger at 50% CPU. Now, it's kind of interesting, that's intuitive, right, if you're doing CPU prediction. But even when you're doing GPU prediction, there's quite a bit of load on the CPU. And so this worked well for both the CPU and GPU runs. We set up the max replicas that the horizontal pod autoscaler would scale to, the TorchServe horizontal pod autoscaler, to capture the max load we were ever going to present, and to make sure that the 95th percentile of latency for that load was less than half a second. So we wanted to have this low latency thing. We didn't want to compromise on that depending on whether you were using ARM or x86 plus GPU. So we compared three approaches. We compared the approach that we're presenting here, which is the right-sized approach. So the resource configuration is dynamic, both in the number of instances and in the configuration of the instances. And so that is the operational model of smart node provisioner with right-sized nodes. We compared that with two things. One is sort of the max size approach. That approach says, look, you know what? I'm just going to create the maximum instance size that I feel comfortable with, that I feel secure is going to be good. I'm not going to, investigate tuning, so I'm going to use x86 plus GPU because that's what I use during training. And I'm going to create a static count of those. That's the maximum I need to be able to serve the peak load that I've tested for. So, and then there's some compromise. So that model is just, make sure everything's already there. Set it and forget it. The compromise is the middle approach, the dynamic fixed size approach, where the nodes are a fixed size of x86 plus GPU that was what you'd used for training. But the number of those nodes is dynamic. So this operational model would be that you've set up, let's say, the cluster autoscaler, and you set it up with one node pool, and this is what the node pool is configured for. So now let's look at the experimental results using this setup. We'll start with Oracle Cloud, OKE. So we set up an Oracle Cloud cluster with 2 statically allocated Ampere ARM CPU nodes for to run cluster management pods, including the Luna pods. And each of those static nodes is a VM standard A1 Flex with 2 OCPUs and 32 gigs. So those cost about 6.8 cents an hour. And then for TorchServe, those 2 deployments of TorchServe each create a minimum of 1 worker pod no matter what the load is presented to the model. And then they scale up depending on how much load there is up to the max. And we set the max that was needed for that load based on the fact that we wanted to satisfy that peak at the fixed latency of less than half a second. So if you look at this chart, we have this sort of request that we made for right size, which is 400 millicores and 4 gigabytes for VGG16. And we got this VM standard A1 Flex that's 1.6 cents an hour to handle that load. When we added in a GPU for the dynamic fixed size and for the max size, now we got the VM GPU 2.1 node, and that cost $1.275 an hour. So that's the kind of choices we made there, and it took 3 of those GPU nodes to hit and handle peak performance at the latency we set. It took 4 of those smaller nodes, CPU nodes, to hit the latency we set. If you look at SqueezeNet, we also asked for 400 millicores, but we asked for only 1 gig of memory to handle the smaller weight size. And we're able to get a smaller instance there, but again, it took 4 of those instances to handle peak load. And again, for the VMs configured, we were able to use the VM GPU 2.1. And one other interesting thing is that we had to ask for more CPU memory when we had added a GPU. So actually, a GPU induces load on the CPU memory for transferring things back and forth. So the first thing we want to say is there any compromise? Are we losing accuracy, or are we losing latency by using the CPU nodes based on ARM rather than using those GPU nodes? And the answer is no, the accuracy was the same between those 2 setups, and the latency met our latency constraints of less than half a second at the 95th percentile. So overall, what was the cost? So this chart shows the table shows the cost per hour for the 3 approaches at 4 operating points which we thought were particularly interesting. The 4 operating points are both models are idle, both models are peak, one of the models is idle and one is peak, and vice versa. And so at those 4 operating points, you see the costs on the table, and on the right-hand side, I guess, is the way from your point of view, you see the same data but presented as the ratio of, in the blue case, the ratio of the dynamic fixed size to the max sized, and in the red case, the right sized to the max size. So what you see here is that you do save quite a bit, even just using the dynamic fixed size at any operating point other than peak. It's quite a bit cheaper than using max size, so great. But you save even more by an order of magnitude by using the right-sized nodes. And by the way, in case you're wondering about this GPU, this is actually an El Cheapo GPU from the standpoint of Oracle. This is their legacy GPUs. They're about to be deprecated, and the new GPUs, the last I checked, were going to be $2.95 an hour. So this is a conservative comparison from that standpoint. So next, let's look at GKE. So for GKE, again, we had the 2 statically allocated Ampere ARM CPU nodes. This is the shape size chosen at GKE. It's T2A standard 2 with 2 vCPUs and 8 gigs, so 7.7 cents an hour. And again, the 2 TorchServe deployments each had 1 pod by default, and then scaled up to more pods as needed to handle the workload. And again, we see down here the VGG16 picked up the T2A standard 2 at 7.7 cents an hour, and then the GPU systems picked up a T4 GPU. So a little bit less powerful GPU than was used at the OKE system, so it took more GPUs to handle the load, but they were quite a bit cheaper as well, so it kind of all works out in an interesting way. And again, on the SqueezeNet, we got smaller instances for the ARM right-sized instances, and then we took the bigger instances for GPU, and so this is kind of the chart is comparable to what we saw previously for OKE. Again, we made sure that we were still getting the same prediction accuracy, and again, we made sure we were getting the same latency with respect to the 95th percentile, hitting below that half a second point. So looking at the cost comparison, we again see the table on the left-hand side showing us the cost for max, dynamic, fixed size, and right size per hour at the 4 operating points we talked about. And again, we see that on the right-hand side in the ratios that dynamic fixed size does save quite a bit of money versus max-sized, but you really save serious money if you're able to go to the right-sized nodes. So finally, let's look at EKS. Here we had 2 statically allocated Graviton2 ARM CPU nodes that ran Luna. And these each were M6G shape with 2 vCPUs and 8 gigabytes. And interestingly, they were also 7.7 cents an hour. So the cloud vendors there's some kind of price comparable thing going on there. Again, we set up TorchServe the way we had previously. And again, you see the kind of number of instances we needed of each type and the types that were chosen for each of these workloads to be able to handle the peak load. Again, we made sure that latency was still okay. We made sure that accuracy was still okay compared between the ARM instances and the x86 plus GPU instances. So here's the cost compared on this cloud vendor at the 4 operating points we've been talking about. Again, the dynamic fixed size saved money, but the right size saved quite a bit more. So you can see here, the story is the same on all 3 cloud vendors. So we've talked about cost, but sometimes cost is not the primary thing. Sometimes operational complexity you care about even more in some ways than cost, because, well, operational complexity also costs you something. So let's look at operational complexity. And looking at operational complexity here, what we're looking at is, if something changes, what do I have to do? And if I have to do something manual, then it's a yes in the box. If it could happen automatically, it's a yes in the box. If I have to do something manual, it's a no in the box. So yes is good, no is bad. So let's look at 3 kinds of changes that might come up and whether they introduce operational complexity for the system. The first is that you might decide to change the maximum number of workers you need. Remember we set the maximum number of workers to handle a certain load with a certain latency. What if my model is really popular, so I actually want to handle a bigger load? So I want more instances than I originally set. Or what if my estimates were lower and I really would like to handle less instances? Well, both dynamic fixed size and right size would respond to that automatically. Whereas the maximum sized setup would require an operator to come and change the number of nodes that are deployed in the cluster. So there's operational complexity there. The second kind of thing that could happen that changes is that the worker size could change. The worker size could change because a new version of the model is rolled out that's either bigger, so you need bigger workers, or smaller, so it would be nice to use a smaller worker. The right-sized system would respond to that automatically. The resource requested for the prod is lower or higher, so it would respond to that, whereas neither dynamic fixed size nor max size would automatically respond to that. And finally, as we said, clouds aren't infinite. When there's instance availability problems, you want a certain instance and you can't get it, or when the offerings change such that the price trade-off changes, there's new offerings, old offerings are deprecated, and so on. So with any of these kind of changes that happen in the cloud, The right-size system would respond to them automatically. If there's not availability of an instance it wants, it uses the next cheapest one that is available. If the offerings change, it picks up those new price points and the new shapes. Whereas neither dynamic fixed size nor max size would automatically respond to that kind of change. So that's the story of this approach, and we found it useful in this case. I wanted to summarize and then talk about one more thing. So in this talk, we've shown that right-sizing inference resources using a load Luna and inferencing compute shapes by choosing ARM CPU-only compute can reduce cloud resource costs significantly. And we showed that measured at 4 operating points for 3 different cloud vendors. And we believe that not only does it not introduce operational complexity, it actually reduces operational complexity because things do change in your environment. And the one more thing I wanted to mention is, hey, that Kubernetes cluster that you deployed Luna on, that might not be your only Kubernetes cluster. You know, you have your Kubernetes cluster that you're doing serving on. Maybe you have a different Kubernetes cluster that you're doing training on. Maybe you have another one that you're doing CI/CD on. So the other question is, how do I kind of interact with all these Kubernetes clusters? And so I wanted to actually mention there's this other product from Alodal called Nova. It's a cluster scheduler that automatically places Kubernetes workloads onto clusters based on policies. So Luna and Nova can work together to simplify Kubernetes resource management. You know, Nova can know whether there's Luna there or not, so it knows whether that cluster auto-scales, and so on. So it's kind of an interesting way for 2 products to work together to help manage Kubernetes. So please give right-sizing a try on your workloads. There's some links to resources here to get started. And thank you very much. And if you have any questions, please let me know. James.
So the compute savings that were available by using the ARM CPU type nodes were significant, but you mentioned a difference in the inferencing approach between like relying on GPUs for doing that versus relying on a CPU only. Are there particular types of inferencing workloads where you know you're not going to lose by not having GPU, or do you have to test that at a high level?
I guess I would say you have to test it, but I guess what I would say, I mean, I'm sure ChatGPT wouldn't run well on CPU only, right? I mean, what I've read is it takes something like 10 A100s or something to serve that model. So I feel like there's models that are kind of mainstream, and these 2 are pretty mainstream models, and these are the kinds of things you'd use. I think they fit on a 16 gig GPU box, which is pretty standard, and they can be easily brought down. So I feel like you probably have to test. I would test, but I also feel like you would almost judge based on how big is the model. I think millions, you probably could serve it on a CPU. Billions, you probably couldn't. And these things are kind of, they're not linear. But yes, I would, to be conservative, I would say test, yeah.
More questions? Okay, well, thank you very much.
Thank you.
We'll have another talk in this room in 15 minutes. Which will be another eBPF talk, this time about the Calico eBPF data plane. So stick around if you're interested in that. And there's also more in Ballroom H and in DevOps Days.
I didn't turn off this mic. I don't know if it's...
Well, so all of the video recording, everything was video recording. And so those videos will be up in a couple weeks, right? And then whether or not the slides are shared up to the presenter.
Okay, yeah, maybe we can share the slides at the Alona website. Let me ask, Madri, what did Madri just, she's heading out the door.
Yeah.
Let me just,
I mean, we're going to email all the presenters afterwards. The slides are online. They're open from the PC interface. Okay.
yeah, I'd love to. Very much.
Very nice. So, thank you.
Oh, my goodness, how
Yep.
fun.
It's a local Pasadena chocolatier, so.
Nice. Thank you very much. Oh, this is my water.
Thanks for sharing that.
Oh,
I've done a fair amount on large ARM servers. So, you know, ARM64 servers that have like 180 cores.
You're right. These are tiny ones.
Yeah.
And it's kind of funny that they're coming. So at the price points they do, the tiny ones, as you get a bigger ARM server, the cost versus x86 is they're not making. x86 is still kind of competitive on cost.
Yeah. Well, the main advantage there actually is we had a really badly written application that kept parking database connections.
Aha.
And that's the one case I knew from the time I worked at Sun, that was the one case where having lots of extra cores, even if they were slow, was really beneficial, because if they're not doing anything, it doesn't matter how slow they are.
Right.
That's
interesting.
Yeah.
That is very interesting. Yeah. I mean, the other thing, just if you're kind of a nerd about these things, is just the power savings.
Yeah.
I know, and that's just the earth goodness.
Yeah.
All right.
Door open. Oh, I mean, you're up in 10 minutes, so you might as well.
Still some time.
Yeah, but I mean, you can just leave it plugged in. That way people know what they're coming into. You've only got 10 minutes. Oh, no, wait, you've got more than 10 minutes. We're on the 15, right?
Yeah,
Right, because it was right, 15 minutes. He ended really early.
That's like, yeah, 10 minutes.
Okay, yeah, right, never mind. Never mind. So you know what they did is, Yeah, this one is actually, this was an experimental model. One of the first i7 ultralight laptops. That was a mistake.
Was it?
Yeah, the CPU really chews up the battery.
Yeah, I have a third battery in this one. Now I have a bigger one. So
Yeah.
it replaces the hard drive, which
Yeah.
there was none. But these Dell batteries, they just inflate.
Yeah.
It's like I was pushing my touchpad out.
Oof.
Replaced it just a couple of weeks ago, so it should be good with power.
Okay. Okay, so let's do, so this goes behind your right ear.
All right, that's fancy. Okay.
Okay.
Hello. Seems to work.
Okay. Okay. So set up, you said no demo or anything that would need internet, so.
Yeah.
Okay.
Ooh.
Okay, that was the vector test. Okay, so usual thing is, as you saw, I'll fill Donahue the questions, so we get them on the recording. And you have until 5:05, including Q&A. So, I'll give you a warning when we're at 55, and then further on if you're still going.
Yeah, when I started the slide is an hour, I was like, oh, I need to fill it in. Now you're telling me it's 15 minutes, so now it's stressing me.
Oh, okay.
No, it's all right. Just give me like a 10 and 5-minute warning if I'm still at work.
Well, I mean, the nice thing about SCaLE, part of SCaLE is to do the Q&A and that sort of thing. So.
Yeah, I'm happy to do that. Hopefully people will have questions. And I can definitely skip over some of the stuff, which is not that interesting.
Calico predates the company. It was an academic project originally.
Yeah, it predates the company. I wasn't there when the company started. I was there later on. But essentially, it was developed by the people who started the company.
Yeah.
So the company is now pretty much maintaining the open source.
Yeah.
And the enterprise product is an extension of that.
Yeah.
So yeah, it's often people don't make the connection between the company and and the project. So yeah.
Which is fun, because Calico was introduced back in the Docker days.
Yeah, it's before Kubernetes, right? It wasn't.
Yeah.
I think it was like open OpenStack or these things, not necessarily for Kubernetes. Now we obviously focus on Kubernetes, and all the rest is kind of like legacy, legacy stuff. But yeah, it's an old project.
Yeah.
By measured by the age of other Kubernetes projects.
Yeah, the Kubernetes universe is sometimes funny for me because prior to Kubernetes I worked on Postgres, but like everything is 15 or 20 years old, and it's based on stuff that's like 40 years old.
Oh well, I still feel like most of my skills are from the 80s.
Yeah.
Kind of job security because not that many people do it these days.
Yeah. Oh well, I had to write COBOL as recently as 2014.
I guess to make good money with COBOL, right?
I mean, I probably would still be doing it if I was still a consultant. There's a lot of money in it, yeah.
Oh, right, yeah.
So yeah.
Yeah. I started working on this like 4 years ago. I was one of those who started the eBPF data plane. So I'm from the beginning of that journey, but not from before that.
Okay. Let's go ahead and get you started. Filtering in, but you know.
Sure.
Welcome everybody to the KCDLA 415 in-depth session. For this one, Thomas Hruby is going to be explaining to us how to use Calico's data plane for eBPF. So you'll learn how to trace all your kernel activity at scale.
Thank you for the introduction.
So welcome.
Yeah, welcome everybody for this late afternoon session. Hopefully you won't be too asleep. Hope you got your coffee. So yeah, I will be talking about Project Calico. I'm not sure how many of you are familiar with Project Calico. Oh, there are some people. Are there any who use the eBPF data plane? Oh, there are some. So in this talk, I will be primarily talking about the eBPF data plane that drives Calico in recent years, but I'll be also talking a little bit more broadly about Calico. So for the few of you who are not familiar with Calico, Calico provides container and networking security, and it these days primarily runs in Kubernetes, so it serves as a CNI for Kubernetes. When you install Kubernetes, you don't have networking, and you need some networking plugins, so Calico can be one of your plugins. But Calico predates Kubernetes, and as we were just talking with Josh here, it started way back then when it was OpenStack and other technologies, but now it's primarily focused on Kubernetes. But it doesn't provide just networking and a networking plugin. What is more important, it provides you with some network policy model, which is yet another plugin that you need for your Kubernetes, because Kubernetes have their own policy model, which is actually younger than the policy model of Calico. And you need something that actually powers that policy model. So Calico has its own policy model, which is a superset of what you can get in Kubernetes, but also implements everything. As I said, superset, so it implements everything that Kubernetes model asks you to do. It is essentially a control plane that takes your policies and observes the cluster and puts the things together and puts it into a data plane that executes. Calico has several data planes or can be used in different environments. As I said, it started way before Kubernetes, and it started with just regular Linux, so it can run on regular Linux in IP tables mode, where all the data plane is provided by the Linux and the Linux kernel. So Calico goes and writes the IP tables rules, and the Linux executes. I will be focusing today mostly on the eBPF data plane, which executes in the kernel, but the kernel only provides the environment for the data plane, but the code and the data plane itself is provided by the project Calico. And we also support and offer a couple more data planes. Cisco contributed VPP, the vector packet processing framework, which is based on Intel's user-space DPDK toolkit. And that was a couple of weeks ago, a blog post about how it works and what are the benefits. So you can go to the Calico project's webpage and read more about that. And we also run in Windows environment. So if you have a cluster that has Windows nodes, Calico can run there. Calico can implement the policies. And what is pretty cool is that Windows is experimenting with eBPF, which is compatible with the Linux eBPF. And so we experiment with that as well. So Calico was supporting the Linux and IP tables since ever. This is where it grew up. I'll take questions after. Yeah, I'll take questions after. Yes. So why is there a need for a new Linux-based data plane? We started this journey some years ago, and we kind of offer it as like a stable or quite stable platform for about 3 years now. But let me reflect first on the IP tables and why we need a new option. So the benefit of IP tables is that it's well understood. I think like everybody came across IP tables at some point. It's been around for, I don't know, 25 years. And it is kind of human readable as much as IP tables can be human readable. Simply you can dump the rules, you can kind of read them, you can kind of see what the rules mean. And so when kuproxy writes the rules into the IP tables, you can kind of go and debug like what kuproxy meant, and when Calico writes in the policies, you can go and kind of see what the policies do and how they are executed. And Linux does the rest of the heavy lifting. It does all the routing, it handles all the protocols, all the corner cases, and all the things that needs a lot of tweaking over those 20, 25 plus years. So this is very robust and very well tested, right? But there are also some downsides. It doesn't necessarily scale. The way the IP tables are designed, there is lots of ON searches, and if you have a cluster where, say, you have thousands of services, and there are such clusters, and we may question the decisions behind that, but if you have lots of services and some of the services happen to be at the end of the list, they take a hit, it is also not extendable. So if you want to change how the IP tables behave, you would need to change the kernel, and that's not easy to do. You would need to write a plugin. Your customers may not want to run those plugins, and it's not super safe. And sometimes even like a simple thing, like if you ask IP tables, give me packets that have the same source as the destination, it's a little tricky to do. It's not impossible, but a little tricky. The next thing is, it is a shared resource. So as I said, Kubernetes are writing through kubeproxy into the IP tables, and Calico is writing into the IP tables, and some of your other tools may be writing into the IP tables. And for that, everybody needs to kind of take care of the consistency, and the rules are being read and written back and forth. And that's not super convenient, and also takes your CPU time. So why to use a new data plane? One of the reasons is better scalability of services. So really, if you have thousands of services in your cluster, and you switch from ON to O1 hashing, then you get a boost. You may get lower latency because of how packets are now shuffled through the kernel, and I will touch on that later on. kubeproxy becomes part of the data plane, or part of the single kind of ecosystem, and therefore there is no clash on the shared resources, and it gives you the option to implement new features which, say, we would not be able to get to like upstream Kubernetes, or we would have to wait for that. So kind of being the lord of the one thing is pretty nice. So let me first, before I dive into the details, kind of give an overview of what actually eBPF is. Some of you probably heard Natalie this morning talking about eBPF, so she already touched on that. So eBPF is in fact kind of like a virtual machine running inside the kernel, but a virtual machine in the Java sense, where it takes code, a bytecode from users, and executes that code, and it does it safely. And safely means that the code is verified by the kernel so that it doesn't do anything that would be harmful for the kernel, so it doesn't access memory outside of what would be allowed. It finishes in real time, and it's sandboxed. Means that it can't really touch what the kernel doesn't allow it to touch. Also, it only runs in certain places in the kernel that are what we call hooks, and those hooks are in well-defined places in the kernel, and in those hooks, the code can ask the kernel to do stuff on its behalf, but only through well-defined API, and certain things you can do in some hooks and certain things you can't. So it is a very flexible tool, but is also safe and allows us to actually run in kernel mode, in kernel code, on customers or users' side without the customers to be afraid of like us causing any harm. I'm sorry? Like what it means, the eBPF? Yeah, the E stands for extended, and BPF is the Berkeley packet filter, but these days it doesn't really mean that much. Yeah, today eBPF is just a name and doesn't have much to do with the ancient BPF, although it can do the same stuff sometimes. So there are two places where we hook the eBPF code primarily. One is at the devices, and the other place is at system calls. So the code that you attach to the devices, and you can do it on the ingress and egress side of the device, allows us to parse the packets and modify the packets. We make console routing, and we can accept drop or forward the packet. So when we forward the packet, we can do it from a device to another device, which effectively means that the IP tables and majority of the network stack in kernel is completely bypassed. And then we can also hook into some system calls. Natalie was talking about it this morning already, but there are certain network-related system calls which allow us to hook in a slightly different way. So we can't just read the arguments of the calls. we can also modify the arguments of the call before the rest of the kernel processes those arguments. So when the application tries to connect, and it wants to connect to location A, we can intercept that and say, no, you really want to connect to location B, and you probably already know where it's going, but I will talk about it a little bit later. So in the generic design of the data plane, when you look at the single node in your cluster, it has a bunch of devices, it has a bunch of pods that are connected to the host namespace through devices, and we attach our BPF programs to the ingress and egress of all the devices that we are interested in. And when a packet comes in, our program has a chance to process the packet and decide where the packet should go next, and can forward it to a pod, or say we are using an IP-IP overlay. So we process the IP-IP packet first. We say, okay, got to go to the tunnel interface, and the program at the tunnel interface has a chance to say where else the packet should continue, right? But when you use Kubernetes, you're probably interested in using services because of simplicity. So when a packet, when a pod or process in a pod wants to connect to a service, how do we decide where stuff should go? Previously, that was decided by kubeproxy as it wrote the rules into the IP tables. But now, we're bypassing the IP tables largely. So who does that? We have to do it. The eBPF data plane has to resolve the services. So let me zoom in at the devices. When you connect a pod to the host network namespace, you usually use a wet device virtual Ethernet, where one end is in the pod, kind of represented the E0 in the pod, and then you have the other end in the host network namespace. And if you use Calico, those devices would be named Kali something, but Calico can also work with different CNIs. So for instance, if you install in EKS and if you use the native EK CNI, these would be called ENI something. So when a packet comes into the pod, just before we go and check whether there's a contract entry. If there is, then we know that it has been already seen and has been vetted, and we just let it in. Otherwise, we run policy. If it's accepted, then we create a contract, and we let the packet in. Otherwise, we drop. When a process is sending packets out of a pod, and if we don't have a contract entry, it means that we haven't seen it yet. We also have to check whether it's actually going to a service, and then we have to pick the backend for the service, and then the rest is pretty much the same. Then we have the host network interfaces. Those are the interfaces, the physical interfaces that connect your node to the outside world, and it's a little similar to what you can see in a pod. We also have to match against contract, but we also have to resolve the services because we may have external traffic hitting node ports. And if we have something that's hitting node ports, we also have to decide whether the packet stays on this node or whether we have to forward it to a different node. So that's our responsibility. Previously has been done by kubeproxy. What we also do at the host endpoint is we run host policies. That's an extension on top of the Kubernetes policy model. Is something that is offered by Calico global policies. So we also let you police like what comes into your node, not just into what comes into your pods. On the egress from a node, it's very similar, but another thing that differs on host interfaces is that we can also hook our programs into XDP. XDP is yet another acronym from the BPF world, which means Express Data Plane, and that allows us to run code super close to the hardware on the ingress into your node. And if you have fancy network cards, I think there's one vendor that has those network cards. You can actually push the code all the way down to the network card. And what it allows us to do is to implement untracked policies. That's yet another feature that Calico has on top of the Kubernetes. So say you want to protect your nodes from some DOS attacks without like running out of resources, and you want to do it as soon as possible so you don't waste computing power on the attack. So you can create an untracked policy, and that is pushed almost, and in some cases, all the way to the hardware. And those packets are dropped very soon, and it's so effective that we actually use this also when you use Calico in IP tables mode. So in IP tables mode, if you have untracked policies, they will be actually executed in eBPF on the XDP hook. So far, I was talking about pods and how we hook into the traffic through the devices, but then we have host network processes. And for host network processes, there's no other way than to go through IP tables. Packets enter IP tables through the output chain, and then the IP tables decide, and the rest of the stack decide where the packets should go. But where should they go if there's no queue proxy, right? So this is the time when we actually use the system calls and we hook into the system call. So when the system call is executed, we can decide that instead of going to the service IP, the packets will actually go to, or the connection will go to the backend. So the network will never see a packet with the host, the network will never see a packet with the service IP. Actually, all the packets will be pod-to-pod IPs, which saves on processing because you don't have to translate every packet, and also saves on the occupancy of a contract table, because instead of needing 2 entries for incoming and outgoing traffic, we just have one simple entry. And this doesn't only work for the host network processes. This is a C group-based hook, and we can hook every process in the system, in the cluster. And it works both for TCP and UDP. So then if you look back at how we send packets out of a pod, if we have this feature enabled, which is enabled by default because we require it for the host networked processes, we can save ourselves some hassle when we resolving every single packet and translating every single packet when it's leaving pods. So far I was talking about intra-cluster traffic, but then we have also traffic that is coming from outside. And one way or another is going to end up as a node port. So a client connects to the node port, and then the data plane needs to decide where the packet is going to stay on the same node and be delivered to the pod on the same node, which is a simple case, or whether it's going to be forwarded. Right? So in the IP tables world, when you forward a packet, you have to do SNAT, because you have to make kind of sure that there is a way for the packets to come back and get translated back to the client. Right? So it is SNATed with the source IP of the node that forwards the packets, then it reaches the destination node, and then it's forwarded to the destination backend pod. But then you lose the source IP of the client, which is pretty inconvenient, right? So imagine that you're writing a policy that says like a set of clients can connect to your front end, or your load balancer can connect to a front end, right? And then the policy sometimes works and sometimes doesn't, and then you start scratching your head and you start refining the policy, then you realize that you pretty much have to allow every node to connect to your front end, right? That's it's not super super nice. Then you have, instead of like a precise policies, then you have like a wide open policy. In the classic Kubernetes, you can deal with that by setting the traffic policy being equal to local. By default, it's a cluster. What it means is that when traffic hits your node port, then it will only forward it to the local pods, right? So this is simple. The IPs of the client will be preserved because there is no forwarding, there is no SNAT, and you have some lower latency because it's not being forwarded, but only if you hit the right node. So if you have a bunch of nodes and the load balancer is not clever enough, you may or may not hit the right node, and then the connections may or may not go through. So in the eBPF-based data plane, we have a different approach. First, SNAT is not super easy to do in eBPF because it is a little tricky, not impossible, but tricky to reserve ports that would not conflict with possible processes running on the same node. So what we do instead is, yeah, client connects, we turn around the packet, but then we put the packet in a tunnel. That is super simple in eBPF, and we've picked VXLAN as the tunnel of our choice, but you can do a different tunnel. The packet gets to the destination node, and we take the packet out of the tunnel. It's the original packet, so we have the client source. And then we deliver the packet to the pod. So that allows you to not worry about the external traffic policy unless you care about the extra hop and the latency associated with the extra hop, because we always preserve the source IP. That allows you to do simpler configuration and more precise policies. But to add some shades of gray in between the white and black of external policy local and cluster, we also have yet another mode. We have to forward the packet to the right node to reach the right pod, but because we have the source IP of the client, we can forward the packet back straight to the client. This is what is called direct server return, DSR, and it's a little dependent on what your network permits, because those packets are suddenly coming from the second node with the first node's IP. So not every network fabric will allow it, but for instance, in Azure AKL, that works great. So we have a third mode, which allows you to forward, but with smaller latency. The underlying network has to allow it, and you don't have to worry that much about configuration. But as I said, use Azure as an example, the Azure health probes are coming from a set IP, and the DSR doesn't really work to go back to that IP. So you can opt out from the DSR for that IP, and then you can have a mix of modes depending on what your needs really are. But eBPF, all is great, but the devil is always in the detail. So with the load balancing at the connect time, I'm not sure whether someone has been to the service mesh presentation yesterday. If you have a service mesh, the service mesh wants to know what's the service and not what's the backend that we picked. So if you use this connect time load balancing, then it doesn't really work with the mesh. But if you already, you can turn it off, because if you already have a mesh, you probably don't worry about shaving off nanoseconds. When we have UDP, you can have connected UDP and we make the decision once. But if you have UDP that is using send message, then we would have to make the service resolution for every packet. So in these cases, we maintain per client affinity, which would be exactly the same if we were not using this connect load balancing. And we avoid ways kind of spraying the entire cluster if your application is sending lots of packets. Sometimes it may not be a problem, but sometimes you care. And then the application selects the backend, but the backend may die. And then your UDP application will be sending stuff to the backend. TCP can resolve those broken connections, but UDP can't. So you can turn off this CTLB thing, and you can also turn it off only for UDP, because usually DNS is the primary use case here. So you have a cluster that reshuffles DNS a lot, you would probably notice it. I said previously that we kind of need this connect-based load balancing for host network applications, but what we can do is, and what we do is we can insert a web pair, a dummy web pair into the host network address space, and then everything that comes from those applications is routed through that web pair, and then we can hook it through eBPF, and then make a decision. But this, everything is kind of like the nuts and bolts of the internals of the data plane, and typically shouldn't be really visible to a user. But as we use as more users are adopting this eBPF data plane for various reasons, what is their perspective actually? So what they like about it, it is fast, and it has new features, but it's a bit confusing for the user because things now work differently than they used to. For instance, it is hard to verify for the user, a knowledgeable user who digs into the data plane, like whether the policies, which are specified as a YAML, are actually translated into exactly the same thing that the user meant. Previously, you could read the IP table rules. You can't do it now. Linux contract is mostly bypassed, so there are some users that have tools that monitor the contract, and suddenly they see a connection with a single packet, for instance, which are corner cases, and that's confusing. Some of the connections, most of the connections you should not even see in the Linux contract. And it's also hard to verify that the services are implemented the way the user would understand. And there are also third-party IP table rules, and these are bypassed, so it may break some legacy setups. To provide some more insights into the data plane, Calico provides a tool called Calico BPF, but it's also accessible straight through the Calico nodes. So if you exec into the Calico node on a particular node, you can execute those commands that will let you inspect the internals of the data plane, the state of the data plane. Let me start with policies. So, as I said, Calico is a control plane that observes the entire cluster and takes your policy that you specify through your YAML file into rules that should be executed by the data plane. Previously, in the IP tables world, all these rules were written into IP tables, so you kind of had them in a single place. These days, with eBPF, it's kind of split across each individual endpoint. So each endpoint carries the rules that apply to that endpoint. And those rules are not just like human readable rules. These are actually compiled into eBPF program. That when we parse the packet, we kind of call into that program. The program decides, okay, is it acceptable or not, and gives us a return value, and then we process the rest of the packet based on that. The catch is that it is bytecode, it's byte blob, and you can go and you can get it out, and you can disassemble that. But that's not human readable, right? So now with the Calico BPF tool, you can go and ask, like, give me the policies in some human readable form. The output looks like that snippet, as that would be more above and below, but it shows the information that you will get. It gives you the rule and the policy that the rule belongs to. That's something you would see in your YAML. It also shows you the action that is being executed and some more human readable description of what the rest of the code is doing. So you can kind of go through the code and verify that the policies are doing what you had in mind. And that's also the actual disassembled code, which is just for those who are crazy enough. Some of the policies don't have encoded IP addresses, because if you have a service that has like tens or hundreds of backends, that would be just silly to put it in like a list of addresses in the code. So what we use is what we call IP sets. We borrow the term from IP tables because it's really like just a set of IPs. So the application, the policy down will show you like what selector applies the rule, and it also shows you, which IP set is used by this program. And then you can go and use the Calico eBPF tool and that IP set identifier to dump the IPs, again, to verify whether Calico understands the cluster in the same way as you understand it. The next thing is verifying how the services look like. And anecdotally, I just had a debugging session yesterday with one user, and this piece of information proved to be super useful. We have two tables. We have a table for front end and a table for back end, which is not surprising. The output kind of groups the front end and the back ends together, shows you what the service IP was, the protocol, was the port, and then it also gives you the information about how many backends are local to the node and how many are remote. It was exactly the piece of information which I used yesterday when I was debugging, and the user was like, it's not picking the backend on that node, so I just dumped that, and it's like, yeah, there's no local backend. In fact, it kind of discovered a bug in Kubernetes because Kubernetes were not telling us the right information, or not the whole information. So then you also have service ID and the backend ID, and as in this example, you can see that some of the services endpoints are in multiple services. I mean, these are just different flavors of the same service. You have a service IP for the service, and you have a node port, and you also have a meta entry for the other nodes for the same node port. So when you dump this, you can also verify that really the data plane is programmed the way that you want it to be programmed. Another thing is routing. As I said, the eBPF data plane can console routing of Linux, but it also needs to have some understanding of the cluster because it's kind of outside the Linux. So this is routes as we understand how the cluster looks like. So it gives you like what CIDR goes to remote pods and what CIDR goes to localhost. And for the local pods, it tells you to what interface it is attached, so that Calico, when it sees a packet to the local pod, can go and straight pick the right interface and send it straight to that interface. Because Calico implements the services, because kubeproxy is not there, we also have to translate all the packets, and we also have to track what the decisions for the services and what were made and what backend belongs to each connection. Therefore, we have to implement our own contract. And normally we maintain a single entry per connection which has all the meta information. And if we do the NATing, we have one more entry that kind of points to this entry for the reverse traffic. So in this case, the kernel's contract is pretty much irrelevant. That's not the source of the truth. When you dump the contract, then this would be a single line, but it wouldn't fit on the screen. Each contract entry is keyed by the 5 tuple, and it carries the information about the connection. In this case, it was a TCP connection that we have seen to be open, and then we have also seen that it's been closed, and then we maintain like how long ago and when it was active so that we can garbage collect the information from the contract table. If you would have nothing, like in this case, then in addition to that entry I described before, you would have another entry which is keyed by the pre-DNAT tuple, and it carries the key of the matching entry with the post-DNAT tuple, and carries various flags. But in our project, we kind of don't believe that everything has to be done in eBPF, and there are certain things that certain other technologies do better. So in this case, for instance, Linux is much better in doing SNAT. It's much better than doing masquerading, and can do it in a safe way. So when you have pods that are connecting to the outside world, in Calico you can annotate their IP pools with the fact that these are going to go outside, and we want to translate the addresses so that the traffic can reach those pods. So in this case, we just let the packets into the Linux kernel, into the IP tables, and let the IP tables do what they can do, and what they can do better than what we can do. And in this case, Linux is obviously maintaining connection tracking, so you will see those contracts. But in our contract, we also have to mark the connection like, yeah, when you see the packets from this connection, just let it go, let it go through. One of the more important features that you can get, or the data you can get from the data plane, is counters. We dump the counters per interface, and you see some obvious things. What is more important here is the error cases. If something's going wrong, and you see that the error cases are non-zero, that's kind of give you a hint that something's going wrong, right? And at some point, Linux kernel changed how the IP devices look like, and then we got connections broken, and suddenly we've seen that there are malformed IP packets, because previously one side of the IP would get just the IP header, and the other side would get also the Ethernet header, and then it changed, and suddenly the packets were So in that case, we immediately spotted what the problem was, and we could mitigate the problem with a fix for certain kernel versions. I haven't mentioned it during the policy dump, but we also maintain counters for every rule. So if you dump the policies, you also get like how many packets hit every single rule, and that can give you some picture of how packets are flowing through the policies and whether they're hitting the policies that you expected them to hit. And the ultimate option is logging. You can turn on debug login, but then you kind of get like a fire hose of logs from all the devices. But it gives you like a super fine-grained information about what's going on with every packet. It's also the piece of the information that the user came to me yesterday, because in that kind of yellowish part, where in this case we have a packet which is not hitting any service. His packet was hitting a service but was not picking a backend. So we kind of knew where to take the debugging from further. And because it's a fire hose, what we've introducing, we have a pending PR for that, is kind of PCAP TCP dump style filters that would only allow you to filter those packets that you are really interested in, because the fire hose in the production server, that's a big overhead. All that stuff goes into a trace pipe, and that's not super fast. So this is a pending
change. And that brings me to what kind of lies in the future of the eBPF data plane. We're currently redesigning the data plane so that we can load the programs faster, because verifier is great, but it's also bloody slow. So we can't load that many programs. And that kind of lies the framework for more flexible feature expansion and will allow us to, for instance, merge those selective logs. And we have to admit it, we still don't support IPv6 in the BPF mode, but this will allow us to also support IPv6 and IPv4-6 dual stack. So, in conclusion, eBPF is a great tool, very flexible, very powerful. We love working with that. And in our enterprise offering, we actually use eBPF to much more like runtime security. But it also disturbs how the packets flow through the system when the BPF is applied to the data plane. So we need to have new tools, and users need to understand how these things have changed. And I hope that this talk contributes a little bit to that education aspect. And I would invite you, everybody, to use Calico and pick the data plane that suits your needs the best, because each of the data planes has its pros and cons, and we support more than one. Thank you very much. Okay, go. Yes, that's contributed. Is there a user space data plane for Calico coming up? It's already there. It's contributed by Cisco. It's not maintained by us per se as a company. And yeah, it's fast processing user space, special cases. Another question? I've seen. If there are no questions, you can catch me later.
And in about 10 minutes in here, we are going to have a Kubernetes home lab setup BOF. Like if you want to run Kubernetes in home or your own small office. This replaces a canceled speaker talk because the speaker couldn't make it. And so a couple of people who have set up Kubernetes in their house are going to talk about how they did it and swap tips, etc.
no one get it? I thought you said you left it.
Oh, no, that's mine.
There you go. So this is a BOF on running home labs, mainly Kubernetes home labs. First, we're going to talk about electrical fire procedures. Kubernetes, running Kubernetes in your home lab.
Birds of a feather.
There is no standard.
I am going to open with a presentation, not because this is a presentation, but you know, just to level set. So I'm going to keep this at just a couple minutes, but why a home lab? There's a number of reasons. We might not all have the same consistent reason, but it doesn't matter. You know, people do this to, you read the list here yourself, save money, regain privacy because you're not comfortable with it, your information and data being up in the cloud, protect yourself from service outages if you don't have reliable access to the cloud. It's also a great learning activity, and for me, this was my favorite. You know, one of the great conveniences in life is being able to access your stuff anywhere, anything, anytime on your own devices, and there are ways to do this on a home lab and remote enable it. But the key thing for me is I'm going to ask you a question. When was the last time you got an opportunity to just have fun, play on the production system at work, and break things? You know, for most people, I think you don't have that experience at work. So a work colleague said this well in a recent tweet. As some of us get older, maybe we lose that sense of curiosity and become afraid to just try stuff out and break things. The home lab's a great opportunity to learn this stuff and grow while you have the joy of being a kid again. And at least for me, that's what it's about. It might be about something different. Now, I gave this talk at an Edge conference. I'm going to skip this. There's a hardware perspective that we will talk about, but you see you have the options of, you have to consider what hardware it's on, but it could be anything from Pis, NUCs, actual servers to control costs, perhaps use servers. Oh, NUCs are cheap x86 boxes. It was called Next Generation something by Intel. Yeah. Yeah. And then other people have made versions, but we can talk about it. And contentions if you're running at home is that other key elements are you do need a firewall router, at least if you know what's out there on the internet. Putting your home lab right out there live direct to the internet with nothing in between it, good luck to you on that. There's open source sources on that. You probably do need storage, and you could use what's called direct attach right in the one box, but if you run more than one, shared storage is desirable. There's a bunch of open source projects. These are a couple ones that are quite popular. And you choose your servers. From a home lab software perspective, there's a lot of cool stuff out there. Some of these are in productivity things like Nextcloud. You basically can do your own Office 365, your own Google suite, and expose it to the internet if you stand these things up and put it through your firewall properly. Obviously blogs, websites, home automation is a big category, home entertainment like Plex, playing music inside your house. Then you can, if you're using this to learn Kubernetes, you can stand up Kubernetes, Docker, whatever you feel you need. And you have options for where you host those apps if you choose to put them there. You could install them directly to the OS, like on Linux as services or apps. You could install Docker first and run them in containers, or you could run them on a container orchestrator like Kubernetes. With that, I'm just going to cut this off and we'll turn it into a legit birds of a feather.
I actually have one thing I kind of want to say. So, home automation, NextWave, OpenZWave, et cetera, et cetera. I run what I consider pretty, decent, stable, hardcore Kubernetes cluster in my basement. I do development off of it. I run quite a lot of what's on here and more. One of the things that I learned over a period of time is even with your home lab, even doing the best that you can, things you want to actually act like production, you definitely do not want to run in your home lab. What do I mean by that? If you have, let's say, a bunch of home automation scripts where lights will turn on and turn off based on certain things, or certain actions will happen if a door opens, probably a bad idea to run in your Kubernetes cluster. That dedicate a single piece of hardware to it, try and use like a managed operating system, like for Home Assistant, they have Haas OS. Please use that, don't use Kubernetes. I am saving you a lot of grief, especially if you have loved ones that you live with and get used to the thing, and then suddenly you forget to upgrade your Kubernetes cluster and your certs expire, and you can see where this is going. Bad. So there are lines. Some people's lines may be different than others. Me, I don't run any 3D, essentially if there's a hardware component and a software component, they're bundled. So I have a dedicated Raspberry Pi that runs Home Assistant. I have a dedicated Raspberry Pi that runs like my 3D printer with Octoprint. But I do run Plex. Plex runs in Kubernetes. I do run things like, oh God, I should just VPN and show, but there's just like different things that I will run in Kubernetes, but the line in the sand that I've drawn is if there's a hardware component, it's gonna be on its own dedicated thing, completely separate, so I can't break it.
I'd like to embellish that. I totally agree, but I'm not saying that it isn't in a home lab. It's just I have bifurcated my home lab. So there's bare metal, which is often on Pis or on low-end x86s. And then my next layer up would be to run them on Docker, and then finally on Kubernetes. And it isn't just that Kubernetes is like that. It's that I get power outages here in California, and to recover the full Kubernetes cluster, the boot time is minutes. Yeah. And on some of these low-end ones, this thing comes back to life just often before you notice. The other thing is that to punch through to hardware I/O devices on Kubernetes, by default, it's locking you out of access for good reasons. It locks you out of direct I/O access. So you have to punch through the abstraction layers, putting them in the modes that the Kubernetes docs tell you is not a good idea because you're running things as root, you're opening up device trees and things. So when it comes to a physical I/O device, the closer to bare metal you are to host that, the better you are. And buy really cheap boxes to run those on. They boot quicker. If you're running a big legit server, those things often have boot times of minutes. Yep. And there's a lot more that can go wrong in that Kubernetes stack, anything on all the layers. So fully agree.
So I kind of want to bounce back off of that. So Home Assistant instance running on a Raspberry Pi. Octopi is running on, Octoprint running on a Raspberry Pi. That makes total sense. Going back to power outages, it's a whole lot easier to have a battery backup to run your Pi running Home Assistant or your Pi running Octoprint so that your print doesn't fail if you lose power. So some small things that are local and still on battery backup. Yeah. But a Kubernetes cluster, yeah, it's battery backed up, but it's battery backed up just so it can shut down and not just bork everything over.
What are your thoughts on your router? Because that's another thing effectively as a package you're running. Are you running a commercial one or do you run an open source?
I run Unify stuff for better or worse. I say for better or worse because sometimes it's amazing and it has the flexibility where I can do whatever I want. It's sweet. And then other times you're trying to figure out if the router supports BGP and you have to find a community post that actually tells you how to enable BGP on their it was painful, but it was still doable. Honestly, the biggest problem is, in my opinion, a bit of a tangent, but Unify moves too fast, breaks a lot of things, and they're inconsistent with like what they patch where. So Unify not open source for the router, but it's so stable and flexible enough where I can deal with the pain. But all of that's also battery backed up and like kind of cool. Justin, do you have anything? I feel like we're taking over.
You can get that deck. I only showed a piece of it, but it was presented at KubeCon Detroit. And that link will get you to the SCAD site and you can download it.
So I can literally talk about my home lab ad nauseum until like tomorrow. Are there questions or thoughts? I could also literally VPN home and show what I'm running or talk about what I've done. I am using the Unify VPN because I didn't want to have to deal with it. Sure, I could use Tailscale, but I didn't want to have to deal with it. The Unify VPN does exactly what I want. I also, this is something that I'm passionate about. My home lab is not the best. It's not even great. It is trash, but it's my trash, and I'm a trash panda about it. Everyone else's home lab, like, it's their own unique trash. No offense to your home labs, but like, if you're running your home lab like production, you know, kudos to you, but this is ultimately, as Steve said, a playground to learn and to break things. Like, the more and more I grow and change in my career, kind of getting existential here, the less and less time I have to actually stay up to date on technology in my job. And I work for the CNCF. So the only way for me to really stay current is to muck around with stuff at home on a weekend. And like, that helps, that keeps me current, and it lets me like dive into a technical problem and be able to feel like I know what I'm doing, but still, like, how else am I gonna learn and stay up to date? Were there other questions? Do you have something? You and then you. Sorry. Yeah. answer to that as well? Okay. I use kind rather than K3s. This is just a personal choice. I like how I can configure kind because that also mirrors kubeatom configs. So that's how I do it, and it's honestly about as lightweight as K3s, maybe a little bit fatter, but that's a holy war that we can not go into. I want to.
Yeah, old enterprise desktops, especially Dell, HP, ultra small form factor machines you can get used. I sold all of my Bitcoin like 8 years ago, and I bought a stack for Kubernetes, and that has paid off more than any of these cryptocurrencies ever did for me. And that was I bought 10 of them, and me and a friend split them, and I think they were $25 per machine. And I was like, Raspberry Pis are cheap. And I was like, but these I could upgrade the memory and hard drives, and they were not ARM processors. So I was like, actually, this was better for me, and I could understand some of the failure domains. And I learned a ton through setting that up very well.
Well, yes. Right now, you try and find the Pi 4B Plus or whatever, the 8 gig one, the one that's like, okay, that right now, like on Amazon, A, it's back ordered, B, it's like $150. You can go on eBay and get what he's talking about now for $120. And then you can expand it, you can add, SSDs, you can do whatever, which is an investment, but you still, out of the box, get, a decent machine.
If anyone is looking for a Pi cluster, let me know. I do know someone selling some. 8 gig Pi 4s.
Okay. So, I'm gonna jump in there with one hardware option that's kind of crazy, but it's what I use, and then I'll hand it to questions. But one thing I found, particularly here in LA, is tons of enterprises used to run colos, and it means they had rack mount servers there's 36 of them, believe it or not, in LA. And at the end of quarters, there's been trends for years where they let their lease go and sell those rack mount servers cheap. I have gotten like Dell servers with 20 plus cores and 196 gig of RAM at an end of a quarter for $99. And they actually are fairly low power because those Xeon chips, they have a TDW envelope, but if you don't load them up, I have physically measured the power. It gets down to 145 watts. It rarely gets over 260. And when you have that, you only need one. You can run whole clusters on that. I think you would. Yeah, I keep it in the garage.
Yeah, the ServerMonkey has sometimes cheap deals on enterprise servers, and they have a warranty, but it's used equipment. But is anybody using VMware? Because I understand VMware 6 for home lab use for a single developer, they'll allow you to do that for free. Proxmon's another one for free. I don't think on Proxmon you can't run a Windows server, can you? But you should use a hypervisor. On Proxmon, can you run?
The hypervisor? Why would I want to slice it up? Oh, because the Linux scheduler for multiple CPUs actually isn't all that effective, and the Linux scheduler isn't necessarily all that effective at these massive CPUs, particularly for NUMA architectures. Call me a shill if you want, but I believe it. Number two, how do you upgrade the OS without taking an outage? So if you're going to run a multi-node Kubernetes cluster in their VMs, I can walk through those and emulate what would happen as a learning experience.
Outage for a home lab. Like, I will take an outage. That's not a problem. It's just, you know, yell upstairs. It's going to be down for 2 hours.
Actually, I want to talk about that really quick. You could be a sicko like me and treat everything in your home lab except for one machine as cattle. Those 3 little x86 boxes, those small form factor ones, I just have them pixie booting off of the main box. And that main box is also the Kubernetes control plane. So those 3 boxes just pick up workloads and go. And like, I don't worry about doing any upgrades. They'll auto upgrade, they'll reboot, repixie, like boot, grab the latest version of Flatcar and go. So like, it also depends on how comfortable you are with stuff just randomly going down. Sure, I'm running a Valheim server on there as well, and it might kick my friends off for about a minute and a half, and oh no, like, you're running a home lab. It's not, you're not trying to get 5 nines at home. Yes, and that's exactly why Home Assistant and Octopi do not live on this Kubernetes cluster. I learned my lesson. Yeah, go.
So the subject of Home Assistant on your Kubernetes cluster. I agree that it's not the best idea, but I have been doing it successfully for about 3 years, and it simplifies the Home Assistant upgrade process for me to just be able to go to Helm file and just go, oh, look, change, click, push to Git, done. So you can do, there are benefits to that, and it can be a lot of fun if you just can say to your partner, sorry, it doesn't work. I think my relationship is stable enough that my partner will not leave me over the lights not working.
So I have a question. So I run a home lab, or I've run home labs on and off for the past like 20 years as I've been in tech. And so my big thing with home labs is bit rot, right? So I set it up, I invest 20 hours getting this badass thing up and running, and then like a service falls over 6 months into it, and I'm like, what the hell did I do? I don't remember how to configure Trafic. Like, how do you deal with bit rot? Where do you keep your documentation? Like, how do you address like, oh, there's a new Kubernetes update, and I literally have to redeploy everything from scratch? Right. Do you want the mic? Yeah. Well, it's for the recording. Yeah.
Okay. So I have a really bad solution. This is cd:/code/home lab. And in there is literally, for me, like on my laptop right now, in there is, I follow this pattern where any like work that I do has a gphy.txt. For those that don't know, my name is Jeffrey Sika, but everyone knows me as Gphy. In there, top down, if I have hardware and nothing else, this is what I have to install assuming I have a vanilla Kubernetes cluster. It literally has the Helm add repo, Helm install, all of the config files, all of the like config for Helm. And this is not sustainable. I should do better, but it also is like the fastest way for me to get something up, having had to wipe an entire machine multiple times. When things break, usually it's because my official stance, never run latest tags in your Kubernetes cluster. Guess what I do? I always run latest. I have image pull policy always. I am the like embodiment of what you should not do, but it's in my home lab and it's my trash and I love it. Also, I just want to update Plex or something. I'll just delete the pod and it'll pull the latest one, and then, you know, if it falls over, I get to debug why. Like, again, there's like this weird sick satisfaction of running this and then breaking it myself and figuring out what's going on. I enjoy that. But when things really bad happen, I was ranting about the BGP thing with Unify. In that gfetxt file, it's like, you have Kubernetes up, cool. Now go and do this so that you can actually run, I already forget. Lets you have a virtual IP pool and then you can route services to the virtual IPs. I forget the thing. It's gonna bother me. Anyways, no, it's not IPVS. It's a project. Virtual IPs, BGP is supported. The other one, MetalLB. So I run MetalLB so I can route to all of these Kubernetes services that I'm running. I need BGP for that to work. So, okay, Kubernetes is running, boom, set up BGP, now I can access all the services. All of this isn't just a giant text file and it's awful. But I also have all of the deployments that, you know, spin up Sonar, Radar, Plex, other things that, you know, we shouldn't talk about on recordings, as well as like, I even have, I once spun up, wow, my brain is failing. ML toolkit for Kubernetes. Kubeflow. I spun that up for like 6 months and was messing around with that. So like all of these different things I just have documented in these files. I don't publish them because also I'll just put secrets in, like, again, don't do as I say, not as I do. I put all of my secrets in plain text on my home lab because I don't care. Go ahead.
Something I've been thinking about as well. Like, you move really fast in your home lab, you're a kid, you're not thinking about the consequences of forgetting later on, and you know, that's kind of something I've been trying to hit the brakes a little bit. Like, I do something cool, and instead of jumping to the next thing, I try to slow down and write about it. So 3 different ways I've looked at it. The first way is like you can do like a home like knowledge base. So like Bookstack's a good one, and you can maintain it. But that's the thing, you start it, and then that's a project to you, and then you're just done with it. You move on to the next thing, you never go back to Bookstack to record it. So it's just more of like a personal, you just gotta slow down and write about it. Another way that I felt that worked for me, that kind of at least helped me not just write about it and record what I was doing, but kind of circle back into like my growth as just overall in general, like even career-wise. Like I started on GitHub pages, so they let you do a free or the static like site and stuff like that. So I do Jekyll, I run that at home, I'll load it up, I'll edit it, and then I'll make a post, and then it's public. So I've actually already, a few instances, like I'll have a friend who wants to like, hey, how'd you do this? I'm like, hey, I actually wrote about that. I don't really remember, and I literally can click through, like copy, I'm like, yeah, here's the commands, and I'm there. I wrote it, it reminds me, and I help him, and then I can talk it to him through what I did and what I was thinking at the time, or any kind of gotchas. And maybe I even missed something, and like, I'll edit this real quick, yeah, okay, cool. And then another one that I've seen more recently, I think I remember the name is called Obsidian. So that could be really cool. And then I forget that there was like a YouTube video, that's how I came across it, but they were using like Git for the backend, and then you could use it as a collab thing. So if you have other people who are interested, that could be another influential way to make you go back and write things down, get people involved, contribute, have it as like a larger than you kind of thing, and that's what really emphasizes you to keep documenting. And then you have this really good, really searchable documentation that helps you just not forget things that you personally have been working on. So that's just kind of what my thoughts on it are. But the Jekyll thing's probably helped me the most out of everything so far.
Anyone in the house that's working on infra just like dumps notes in there. Discord search isn't great, but it's something. That's really not saying much.
Anybody discovered any tools, like I'll throw one out there for monitoring of these if something died, if you're running a few things, but this uptime Kuma is pretty cool for verifying that things are still running before you just discover something doesn't work and then shooting you some notification. But I'm interested in any cool tools that people have found useful in home lab.
One I really like to plug, it's a little, it's a controller, I guess it's not really a full operator. It's called external MDNS. It'll take your ingresses and services and just share them out via MDNS, so you don't have to like deal with figuring out, like remembering IPs or service advertisement within your home network. That, and you can run Avahi just in containers. That's how I get the nodes into local DNS. Both really helpful. Also, Grafana Labs, I don't know if anyone here from Grafana Labs, they have a fairly generous free tier. So like that plus Grafana Agent gives me a monitoring stack that I don't have to pay for.
So I actually use Core DNS for my home DNS, route everything to that. So my DNS records are also attached to any of the services that I create. Again, it's my trash and I love it. But that way, I have a custom TLD that every computer on my home can get to. And because, again, going back to my wife, she's obsessed with Tron Legacy, so it's .grid. If you are at if you're at my house, you can go to things like plex.grid or the.grid, and it comes up with like Heimdall with everything, you know, up front. Like everything is .grid. But also, you know, with the DNS, you can also do things like pi-hole filtering. Everything goes through a pi-hole. Well, not pi-hole, actually, Core DNS has a plugin called ads. But the same DNS server that Kubernetes is powering my Kubernetes cluster is also, like, every client on my network is hitting that as well. It's just kind of interesting. All right, I think Justin has a cool thing, at least something to talk about.
So I didn't see anything in the slides about just having fun. I mean, that's what I do it. All of my I've been running home theater PCs since 2003, Myth TV. My first full talk was actually at SCaLE, Myth TV 2009. And so all of my home lab stuff is not in Kubernetes, like no. Almost none of it is in containers. It is machines, it is Raspberry Pis. These are my fun toys here. So kubernetes.dev is what this was dubbed with a C. Will redirect you to this blog post, which if you wanted to see the hardware and everything. I built this, I work at Amazon, I work on EKS Anywhere, which is our on-prem stuff, and we were building bare metal support, and I was like, I want a home lab for this. Sure, I could get the NUCs, I could get the Raspberry Pis. Those are all really practical solutions. And I'm like, no, like I want this to look cool. I want to try some things with it. And so this is in total like 4 terabytes of storage, 128 gigs of RAM, and 32 cores, all Intel 86. They're all i7s. The boards, they're all listed here in the blog post. It costs about $6,000. You know, this is marketing money at that point. But the fun thing that I learned doing this was not only re-up my soldering skills, but things like these lightboard displays are run by MicroPython boards in there, and those show up as a volume on the computers. So I can run a Kubernetes deployment that changes the picture here, and there's LEDs on the back too, so I can change what the LEDs do. So they're all programmable, and I just have a little Python script that shoves in a Docker container and then mounts the volume and rewrites it. And it's like, cool. Like I can, like the weird fun things like that, like all my old actual production on-prem stuff, like I was upgrading firmware with daemon sets on bare metal, because I was like, you know what, like I don't want to shove in a USB drive. But that was, I thought this was fun. I do have Raspberry Pi clusters. Most of my stuff runs off of Synology at home as like my home lab. I do think that we all need to like share Plex friend servers or something, because it seems like a lot of people have those. But I've been doing home theater PC stuff forever, and so I always do home labs just for the fun of it, to learn things, to see how to automate and kind of push some of the weird limits of what people do on-prem, because that's, home labs are those dumpster fires of do whatever, but I keep all my stuff my wife and family depend on separately. So yeah, I had this in my car. I cannot connect it to the internet right now, so it actually won't pull up right now. But it is the most expensive Rickroll as far as I know, because the nodes are named never going to give you up. So yeah, it's always a fun thing to show off. But right now, for some reason, it won't pull a Docker image. So. It's in the blog post, but it's from a random company, and the boards are called LP179s. They're the worst named boards in the world, but they're meant for signage, actually, for like for enterprise signage, because they have out-of-band management on them and dual NICs. And so I was like, I wanted something in a Pico ITX form to try to build this, because I had a cube that I wanted to start with. And so I was like, it needs to fit in this. I want to fit 4 of them. And so yeah, I found these enterprise signage boards, and that's what I started with. And then everything else was just custom tearing apart an old Apple cube. Yeah, Pico ITX was the smallest I found, and EKS Anywhere doesn't support ARM right now, or at least it didn't, and so I couldn't run Raspberry Pis. I'm like, I wanted something with a little bit more horsepower to show off some things, and then it has over 1,000 LEDs in it, because that's fun. Has anyone tried Talos? Sidero Labs has a like provisioner for bare metal. They have like a startup, like it's a subscription, but it is WireGuard back to them for management, and it does all the monitoring, and it gives you logs, it gives you the whole provisioning stack, which I think is really neat. It's probably one of the latest softwares that like made me happy. I was like, oh, this was really cool, because it just, you boot it and it WireGuards back to them, and then it just shows up on their web console. And I was like, wait a minute, what? Like, it was that easy for bare metal? And then you just drag it and you say, make those a Kubernetes cluster. And it did. I was like, no way. And so I was really impressed with that as like a home lab user for bare metal stuff.
Let me throw out a quickie
Yeah, I had a question for your home lab. You mentioned pixie booting 3 boxes. Do you have any maybe recommendation for how you handle, so very particular use case of like, I'm thinking dynamic network visualization, so keeping track of what you can see with boxes. Oh, no worries. Okay. Yeah, so for your home lab with, you mentioned 3 boxes, pixie booting. Very specific question, but I'm curious, do you use any solution for like a network visualization with the network being dynamic, like just keeping track of what boxes are online, what's running? But okay. Nice. Okay, cool, thank you.
So I guess everyone here is already in this world where you have your home lab. I'm at the point where I'm kind of outgrowing like Rancher Desktop and Docker Desktop. I want to do something hardware. And I gotta know what's the recommended first step into that world, right? Like, so I've got a old desktop and I'm like, okay, I don't want to sell it. I don't want to give it away. It's just sitting here doing nothing. I want to run a home lab on this thing. Is it, someone had mentioned earlier, Proxmox, put Proxmox on there, cut it up into different servers, set it up. Is it installing all the Kubernetes pieces piecemeal? Or is there, you know, is there an application that I should be using? Like, what's that first step that I should be looking at?
It's an itch that you'll just never be able to fully scratch once you start, assuming you're sick in the head like we are. However, the real answer is one that you're not going to like, but it's true. What are you most interested in? Are you interested in learning Kubernetes? Hit up Kelsey's Kubernetes the hard way if you really don't like yourself. Or you can just look up, you know, bootstrap Kubernetes on your own. Or honestly, you could just run kind on that machine and then you have a Kubernetes cluster. I just don't recommend it. Like there's K3S as well. There's so many things you can do, like the path. It comes down to, why do you want to do this? Like, what are you interested in learning the most? And then you just kind of go down that rabbit hole, because like there is no right answer. Do you want to learn about containers? You don't even need Kubernetes for that. You can install containerd and then just, spin stuff up. Like, I know friends that are very, very well-known Kubernetes contributors. You would expect them, hey, Kubernetes at home? Screw that. They have one box. They do not run anything in Kubernetes. It's just a bunch of containerd scripts. The end. Why? Because they don't want the complexity. They don't have that like desire to break things and figure it out. So it depends on what you want, what you're interested in.
If you are looking for something to learn, Awesome Self-Hosted is one I always point people to because there's so many cool things that you never knew you could run. If you're just like, hey, I want to try something and I don't know. Because a lot of people are just like, I don't know where to start. Like an Nginx container didn't matter. They want like, I want something I can use, something I can try, and maybe throw it away. And Self-Hosted, the Awesome Self-Hosted list has thousands of different pieces of software that are varying degrees of they work or they don't. Some of them may not have containers. All of these will never have a Kubernetes manifest. So you are going to do some things manually, but it kind of gives you some starting point of like, I don't know what I want to run, and maybe I don't write the software myself, so let me just find something to run and try.
Yeah. So I've heard this is a very difficult problem. Have you ever tried self-hosting your own email server? Oh, yeah? No? Yes? Okay. 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 Gotcha. Oh.
So as far as I'm aware, TrueNAS SCaLE has some kind of integration with Kubernetes in some way, in which you're able to like build containers on there somehow. Are any of you familiar with that? TrueNAS SCaLE has something kind of integration with Kubernetes, and you can build containers and services on there through, I think, Helm charts. Okay. Yeah, Debian Linux, yeah.
Yeah. Oh, did you have something?
No, I just thought of something.
Actually, do you run like any of your own DevOps platform or like GitLab or something for your own projects, or do you run that out of band outside of your own home lab? Or? Oh, I've never heard of it.
I was just going to mention there is, I mean, you can run self-hosted runners for GitHub, and there's a controller for Kubernetes that you can do that. I mean, there are some security risks with running self-hosted runners from public repos, of course, and you can go read GitHub, yeah, the documentation on that. But that's an option too.
Oh, no, sir. I mean, I think about Home Assistant. I think about I am running automations. I want, something to motion detection, turn on a light if it's over this, certain time and I'm out, turn on, again, lights, security, maybe some, like I run an NVR thing so it detects if I'm in a room, turns the lights on as well, just weird automation. But you can do other things with Hugin, like I had it scraping Craigslist for an area. Hugin lets you set inputs, processes, and outputs, I think is a good way of putting it. It's like Node-RED, but easier. So like, I used Hugin to get a really cheap camper for some remote property that my buddy and I own. I think that's a cool story, and I run that on my home lab. Like, I can actually say this home lab saved me a whole bunch of money because it found us the cheapest camper we could possibly find. That's cool. No. So you can set it, in this case, I created a thing that would, on an interval, hit Craigslist, look for new entries based on my search criteria, and if something popped up, send me a Discord message. It is self-hosted. It is self-hosted if this then that. But I mean, the reason I say it's different from Home Assistant, yes, okay, technically I could have Home Assistant do that, but it's like so backwards versus Hugin. That was just like, when it comes to fun stories and like conversation dying out, fun thing.
I'll throw out one that's new to me in the sense I recently discovered it. I can't contend I've got it fully operational, but there's something called Open MQTT Gateway. Yep. And if you use Z-Wave, the implementation commonly used with Home Assistant routes it through an MQTT broker, but you can use other things. And this Open MQTT Gateway runs on these little ESP32 boxes. They're sort of like an Arduino thing that could be found for $8 to less $15 on Amazon or AliExpress. And it's a software-defined radio with plugins for this open source project called RTL 433. There's hundreds of these things on there. It will pick up temperature sensors in both ways, like weather ones or barbecue thermometers. It picks up a lot of vehicles' tire pressure sensors, which you could use to tell you without paying up with the deluxe version of the car that would tell you which tire is low. You could graph the actual tire pressures on your car. I know it supports Fords and Hondas, but I think there's more. And Open MQTT Gateway. And it's in the Arduino class, so you aren't running that on Kubernetes. You blow it into this little device that's the size of a stick of gum. And it has the radio built in. And it's just standalone. It will bond to your Wi-Fi in the typical implementations. And we'll punch it through to whatever home assistant or whatever you've got to use in automations. Or you can just use the data to write programs for web pages for iPads to display this.
I'm not running my home lab right now, but I was running one for quite a while. And it was actually for a more serious purpose, which was I was working on a couple of pieces of software designed to provide high availability for things. And I have yet to find any piece of cloud software that can simulate a hardware failure in the way that hardware failures actually happen. And so having a rack of boards, on my spare desk, where I could literally just pull the power cord or the network card out of one of those boards, allowed me to actually test for a lot of hardware failures, because there's weird things that happen in real hardware failures where the network is still accepting messages even though there's not anything on the other end. And that doesn't really happen in testing frameworks. And so it was really useful for doing that.
At least this is what's currently running in the default namespace of the home lab. Fun things of note, I mentioned NVR. I don't know what that stands for, I can never remember, but long story short, like video recognition. Sorry, what's the network video recorder? Hey, Steve. Got you. So I mentioned I'm running Frigate to detect if I'm in a room or a garage, and if I'm in there, turn on or off the lights. That's better than motion detection because motion detectors kind of suck actually when it comes to if you're still in the room after 5 minutes, it'll just think that you're part of the scenery. Heimdall is an interesting project. Think of it like just a dumb front end for building and linking to other services. It's kind of neat. I mentioned Hugin. I haven't done anything with Monica yet, but it's this, think like a personal CRM, more like, you know, a phone book almost, but a little bit more metadata around people. Plex, hopefully everyone knows Plex. Radar and Sonar, think managing TV and movie shows that you may or may not have. Restreamer is actually, think like an open source version of, I don't want to say Twitch, but you can stream to it and then it can stream out to other places. Stupid nerd flexy thing that I did, but I also think it's super cool. We had a LAN party, my buddies and I, a couple weeks ago, and we all installed OBS, streamed to Restreamer, and then every 30 seconds on the TV in front of us, our perspectives would change because we were all playing, you know, Viking or Valheim, which is like Viking Minecraft. So every 30 seconds, each of us would like see what the other person was doing. And it was just like kind of a cool thing. If you know what news groups are, you are old blood, but that's still how I may or may not grab things. Who here uses Steam? Like video game Steam? Who has other people that may come and download things when they're on your home network, like a LAN party? Yeah, so there's the Steam Cache project, and I like it, except again, I like messing with stuff, and if something is just a little bit not what I want, I'll build it myself. So I built this thing called Tenta, which is just a Steam cache. Does exactly what Steam caches do, but it exposes all of the metrics in a Prometheus fashion. So I can actually like no joke, this is, I just wanted to dashboard how much bandwidth I'm saving, and I could not do that with the other Steam cache. Yes, GFE Tenta. Valheim, and then I have a bunch of cameras all around my house, and I wanted to pipe them into Frigate, but they're Wise cameras, and I didn't want to flash their firmware, so there's a project called WiseBridge. Whee! Also, I'm running Cert Manager locally, because I want SSL everywhere and I'm weird. I was running an instance of Spark because I'm a former academic and I like messing around with stuff. Again, I was messing around with Kubeflow. And though I do say I am okay with everything being a trash fire, I do back stuff up regularly up to GCS bucket, so I have Valero installed. Oh, and a Prometheus monitoring stack. That's me. Sorry, what? Is Valheim Plus? I have no idea. If Caslin is nodding, I trust it. We should actually.